You see my, oh, I lost where you guys went.
Yeah, we can see your screen, Paul.
All right. Where did you go though? I don't see the people anymore. I don't know where you went. Where's Spence? Huh? That's all right. I guess I won't be able to see you. That's fine. All right. So my name is Paul Reith. I'm from UNC Chapel Hill at a research institute called RENCI. And like Ellie pointed out, I am the PI of a project called Fabric, which many of you have maybe heard of, but maybe many of you haven't. And I've been given about 15 minutes or less than that now to just give you just a brief high-level overview of what it is, and maybe entice you to get an account and try to experiment with it. And I'm going to highlight several things that are kind of related to science DMZs and P4-DPDK as this meeting is supposed to be for. So, um, so Fabric, it was founded by the NSF in 2019 as a mid-scale RI1 project. We had 4 years to build it. You'll see in a minute when I show you what it is. It was quite a complicated feat to get it going. Um, so in 2023, in the fall we finished the construction phase and moved to the official operations phase, and we have funding until the fall of 2027. Currently at funding till the fall of 2027 to keep it open for business and let you use it and do experiments and write papers and so forth. It's led by RENCI, which myself, the PI. There's 5 other core institutions. So besides RENCI, there's University of Kentucky, Clemson University, University of Illinois, and the Department of Energy's Energy Sciences Network. All of us come together to contribute to this large project. Also, dozens and dozens of other collaborators that host our sites and give us access to different types of resources. Um, so it's a mid-scale RI1 infrastructure. The purpose is to empower researchers to securely prototype and validate like really disruptive network designs in an environment that closely emulates the real systems that drive modern distributed applications today. You can kind of think of Fabric as a scientific instrument or a laboratory that enables experimentation with new paradigms of distributed applications and internet protocols. But the key thing is that these applications and protocols can now run both across the network, but also within the network. And that's the key. It's composed of 35 sites. There's 34 listed on this slide here, but there's 30 domestic Fabric sites in the US. And I'll show you a map in a minute. There's 4 international sites, so 3 of them in Europe and 1 in Japan. And there's one bonus one that the Sienna company has purchased for us, and it actually travels around to different kind of events. So it's been at the Supercomputing Conference the last couple of years, and then the OFC conference as well. I was in fact at OFC a couple of weeks ago in San Francisco, and a lot of people do experiments at these different conferences. What Fabric does is it allows like really it provides a deep in-network programmability. So you're talking about compute and storage, which is kind of the obvious things, but then also SDN switchers and routers that can do P4, smart NICs that could do DPDK at 100 gigabits, sometimes at 100 gigabit bandwidth. Soon we're going to have smart NICs with DPUs, so Bluefield 3 NICs that Ellie and Jorge are also involved with, helping us, or we're doing that as part of a grant with them. We have FPGAs that have 100 gig NICs on them. We have GPUs spread out all across the thing, the test bed. There's dedicated optical links, 100 gigabit plus dedicated optical links, including international circuits. And it's integrated with all the HPC centers, clouds and wireless test beds, commercial clouds, your campus potentially, large instruments, and the internet. So, like I said, it has a worldwide footprint, 35 sites, dedicated network capacity. Each location, so each blue dot on this map is a rack or a cluster that is an OpenStack cloud where experimenters can deploy like private routers and switches and other sort of compute and storage that support their applications, their distributed applications. But inside each of these sites, we have, like I mentioned, a bunch of advanced accelerators. So at these sites, there's GPUs and FPGAs and programmable NICs and P4 switches and these kinds of things that you can incorporate into your topology. Um, the user-controlled resources at these sites are connected with dedicated network circuits. The blue links on this map are dedicated 100 gigabit layer 1 connections that we control, and then we can divvy out to the different users. The orange ring is 1.2 terabit per second ring that we control, and we can allocate to the users. Now, no one user is probably going to use 1.2 terabits, but what that allows us to do is give several different people at the same time 100 gigabit network connection, and they won't interfere with each other, and they can run experiments as if they have dedicated 100 gig connections. Also worth pointing out here is on this map, the orange stars are some of the original, what we call facility ports, or these are external facilities that are connected to Fabric, and you can use things in these facilities and connect them together using Fabric. So these are a lot of times supercomputing centers, but also other NSF test beds like Chameleon and Cloud Lab and the Power test beds and Sphere and these kinds of things. The orange ones on the list here are just some of the first ones we got up and going. We currently have dozens and dozens of these external connections. Many of them are to dedicated like data centers, but some of them are just to like someone's lab at some university. So if you're interested, you can think of these kind of like a science DMZ. So if you have a science DMZ and you think that you have something interesting, some interesting instrument or compute center or data repository or what have you at your university, we can work with you to enable connecting that to Fabric and therefore to everything else that is also connected to Fabric. Yeah. So like, why are we doing this? So the observation here is that for decades, we've built really cool instruments and data centers and public clouds, and your campuses are all built up with all this computation and networking. But applications are still limited to running at the edge of the network. And there's this growing emphasis on edge core cloud paradigm of programming distributed applications that don't really reside in any one place. They kind of flow throughout the network. And the observation is that although we have lots of really interesting resources all over at the edges, we don't really have interesting resources in the network that users can researchers can use and do experiment with and create prototypes of. So that was our observation and our goal and what we did is we built Fabric, and Fabric allows you to run applications anywhere. So now you can run them at the campus, at the edge, in the cloud, or in the places where routers and switches are typically found today. So this allows you to do interesting things with in-network processing or intelligent caching of data or distributed AI or many other things that all of our users and all of you out there that might want to use this are going to invent and surprise us all. The other thing that was important about Fabric is to have it scale both geographically and in terms of performance. So I mentioned that there's 35 sites connected with mostly 100 gig plus dedicated layer 1 circuits. And it also connects the real facilities that you already use, such as NSF clouds and compute clusters and supercomputing centers and so forth, and also your campuses. And the point here is that you can deploy production prototypes or different experimental things in a sandbox where the network part is sandboxed, but the real facilities on the edge are the real facilities. So you can actually deploy experimental prototypes in parallel to your real deployments at the scale of your real deployments. And that's the point of what we're trying to do. Just quickly to go over users and use cases, I've picked a few. I don't have a huge amount of time to talk about it, but I picked a few that are be relevant to this group. So one is just like P4 programming generally. So we have several different ways you can do P4 programming on Fabric. The easiest and most available one is just using BMV2 software switches. And Ellie and Jorge have designed a bunch of like learning modules that use this. As Ellie's going to talk about in a minute, and I think you're going to learn all about today, you can run P4 using DPDK, and we have in all the Fabric sites have ConnectX 5 and ConnectX 6 smart NICs that support DPDK, and you can get either like a dedicated ConnectX 6 with 200 gig ports on it that you just own and use and can do whatever you want with, all the way from that type of performance to what we have are what we call shared NICs. So these are SIOV virtual functions that are on a shared network card that's shared amongst several users. And these will also run DPDK. So if you need a whole bunch of NICs to emulate like maybe a P4 switch, you can do that. And people are getting really good performance. I'm always surprised when they use DPDK because they're getting near line rate performance while running things in software. So it's really exciting. One step more complicated than that is we have these Xilinx FPGAs. So these are network cards that have two 100 gig ports on them. And we have a couple different groups, one at ESNet and one at Northeastern University, that have these workflows where you can actually run P4 programs on the Xilinx FPGA. And what's interesting about this is that you can actually have P4 programs that run in the hardware, and you never actually have to go to user space like you do with DPDK. And then finally, we have actual Tofino switches, P4 switches that are in various places, and you can use those, get them allocated to your experiment, and then program them, which is really exciting. And switching over to the other side and talking about like how does Fabric do something that looks like a Science DMZ? Well, we have this really interesting experiment at Rutgers University. So Rutgers has one of our sites, but you're not required to have a site to do this, but they have a cryo-EM microscope. And what they've done is they've connected the cryo-EM microscope to Fabric using what we call a facility port. And they can now deploy something they call a cloudlet. They deploy that anywhere they want inside of Fabric. Usually they use one of the sites that is closest to Rutgers University, but it can really run anywhere. And they can then connect to their microscope, control the microscope remotely from the cloudlet that's on Fabric, and then actually pull data from the microscope into Fabric. And they usually move it over to Pittsburgh Supercomputing Center, but you can really connect it to anything that's also connected to Fabric. And they have this mechanism which they're controlling the microscope and moving data back and forth between the computing center using their packaged software called a cloudlet. Interesting though is that one of the points here is to have this package such that other groups can deploy the cloudlet to connect their cryo-EM microscopes. And we have the first instance of that is sort of on their way. So University of Wisconsin has a cryo-EM microscope, and we're working with them to use the Rutgers cloudlet to control the Wisconsin cryo microscope, and they just deploy their own cloudlet wherever they want and can do that. So this is really exciting. It got the best paper award at PERC last summer. So it's one of the ones we like to show off a bit. Yeah. And last, I would just highlight that like many of the things that you're learning today, so these P4 educational laboratory that Jorge and Ele have built, they have a whole sophisticated system that existed before Fabric, but they've ported many of their laboratory materials to Fabric. So someone with a Fabric account can actually run the University of South Carolina Cyber Infrastructure Lab modules to learn about P4. And I'll highlight the NSF Cyber Training Award that we have that Fabric's partly on, and then Jorge and Ele are also part of that as well. And what this is going to do is we're going to deploy NVIDIA Bluefield 3 DPU enabled NICs. These are the ones with the hardware encryption. And we're going to deploy them into Fabric. This is coming soon. We're like getting close to putting into order, and we've already have a proof of concept of it working. So if you're interested in Bluefield 3s with DPUs, stay tuned. We should have these maybe in the fall, all ready for you to go. And Jorge and Eli are working with us to make those work. Couple just really simple metrics that you know about what we're doing. So reiterate, we're like about a year and a half into our operations phase, and we have 2.5 more years of funding already, hopefully more after that. But we have, getting close to 50 known publications. Now, there's probably a lot more than that. These are just the ones we found. And if you're already a user and you've written a paper, please tell us about it, and we'd like to put it on the list. We have over 2,000 total accounts that people have used Fabric. About every month, we have somewhere between 100 and 300 active users that are using Fabric for some reason or another. Most of those are educational users, but it's about, it's 40-60, so it's, pretty even numbers between research and education. We have, over 200 different organizations represented, 176 different .edus, so it's a wide breadth of universities that are using this. We have, about 250 projects total, and what's interesting is most of the projects are research projects, but most of the users are education users. So if you want to use this for education, you can. If you want to use it for research, there's a lot of research going on. And if I can go to the next slide somehow. So upcoming events, we have, if you want to get started, we have webinars monthly. We have some of them are tips and tricks from our team. They're showing how to use Fabric. Others are user stories. So I think if you want to see what people are doing, you can click on some of the user story ones. There's also a YouTube channel, a Fabric testbed YouTube channel, where you can see many of the old ones. So you should check that out. We also have a workshop twice a year that we call KNIT, and the next one is in October in Salt Lake City. So if you're interested in that, go to our web pages and stuff, and you can see more information about it and sign up for it and attend. And that's all the time I have. So thank you. If you want, and I'll tell you a little bit about getting an account. If you go to whatisfabric.net, or if you go to fabric-testbed.net, you can land on our portal. There's a button that says sign up and create an account. You should do that. If you are a professor or a research staff member somewhere, you can become a project lead and create your own project and start using Fabric. If you're a student, you'll probably need a professor to work with you, and that professor can have the project and kind of work with you. If you want to play with it for a short amount of time, you can go create an account and you can contact me, and we can put you in a tutorial project and let you do some of the tutorials for a little bit, but then we'll need to get you into a bigger project. So, and Jorge and LA, who are running this workshop today, know quite a bit about Fabric, so they're a good resource as well. So that's what I had. That's my 15 minutes. Went a little bit over, it looks like. So I guess we can take a couple questions, or Ellie, how do you want to run it?
Yes, sounds good. Thank you. That was great. If there are any questions, please, you can unmute yourself and ask, or you can post in the chat.
I have to open the chat if I'm going to do that. Let's see, chat. Okay. Yeah, and please do create an account. It's free, and NSF pays for you to do this. We want people to use this. Sure. And especially after today, I saw the rest of your agenda for today. I think there's a whole bunch of examples of things that you will likely be able to use Fabric to do some of your examples if you wanted to experiment even further.
Yes,
You
yes.
might even be doing that anyway. I don't know what they have planned for you.
Yeah, we have some demos that we already did on Fabric, so they will be able to see it as well, like
Okay.
on the Fabric itself. So, right, I don't see any question. Well, thank you, Paul. If you guys have any question, again, feel free to post them in the chat. I will try to answer if Paul has to step out. Otherwise, we can also forward the questions to Paul, and he will be able to help.
Yeah.
Right.
We have all sorts of online help and a forum where you can ask questions and all sorts of things. So if you want more information, just go to our website and we can get you set up.
Sounds good. Thank you so much, Paul.
All right.
All right. So next we will let's go back to the agenda. So next we're gonna look at a set of slides just describing P4 and DPDK. So these are the main technologies that we will be using today in our hands-on session later. So again, as you can see, the slides are uploaded to the website. So you have all the resources there. So let me make sure my screen is shared. All right. All right, so in this set of slides, I'm going to talk first about an overview of packet processing. How does packet processing work in traditionally in the kernel? Then what is kernel bypass and DPDK? Followed by that, we're going to look briefly on the P4 language and how you can combine it with DPDK. And then we will conclude with some applications that can be done with P4 and with SmartNICs. So let's get started with packet processing on end hosts. How does it work? So you have the user space where your application is running, and then on the kernel space, you have the NIC driver and memory where you would store your packets. And so the NIC would pre-allocate the kernel buffers, right? The memory buffers here where the packets will be stored. And then it will also pre-allocate those transmit, the TX and RX rings or queues. Now, those queues here will be holding pointers to where the buffer is in the memory, right? Or where the packet is in the memory. Now, when the packet is received on the hardware of the NIC, there's also a queue, a hardware-based queue there, but there will be a direct memory access that would copy that packet to the memory buffer. And after that, the NIC will generate an interrupt to tell the driver that there's new packets available for processing. So that's how every time we receive a packet, these are the steps that are happening so that you can consume that packet later on in the user space. So with all of that, there's a lot of overhead happening. And to go a little bit deeper, so the CPU has to pause the process whenever it receives an interrupt from the NIC. So if it is executing some process, it has to pause that execution. And then it has to do a context switch. So it will move from user space to the kernel space. Now, this is a very costly operation in terms of latency. Then after that, it would acknowledge this scheduling, and then it would resume back to user space to continue the previous task it was executing. So we can see here, we are now doing another context switch. Now, once the CPU is free at the user space there, it's going to move back to the kernel space. And there it would allocate packet data structure for that packet. It will remove the Ethernet header and then pass the packet to the network stack. And potentially you can have multiple packets coming at the same time. So you have to do that for all the packets in the buffer. So that's typically how you process packets in the Linux kernel. Now, why is this problematic for high-speed networks? Well, first, we have too many context switches, i.e. moving from user space to kernel space and vice versa. That would pollute the CPU cache. We also have a lot of interrupts that are happening per packet, even though there are some optimization in the kernel, like NAPI, for example, where you can kind of batch multiple packets, but it's still, you are doing interrupts every now and then, and that would cause all the context switches that we talked about in the previous slide. The packet data is being dynamically allocated, and also there's packet copy between the kernel and user space. So as you can see, it was in the, when we received the packet, we copied into the kernel, and then we have to copy it back to the user space for processing by the application. So these 4 items here would cause overhead that would degrade the performance. So how much can we expect in terms of performance? So if you see in this table here, we have the link capacity from 10 megabits per second to all the way to 100 gigabits per second. If you are assuming that the packet sizes are 64 bytes, small packet sizes, then the time budget per packet to achieve this line rate, for example, 10 megabits, here is 51,000 nanosecond. So that's still okay, right? Even with all this overhead, we can still get 10 megabits per second because this is a relatively large number. But then as you go beyond the 1 gig and 10 gigs specifically, like with the 100 gig, you have 5 nanosecond to basically, that's the most your packet can stay there, right? To achieve this 100 gigabits per second. And that's why with all this overhead that we have, you will not be able just to be able to achieve 100 gigabits per second. It's not possible with the current traditional stack. So what's the solution for that? One of the solutions is to bypass the kernel entirely. Okay, we call it kernel bypass, and the idea is to avoid all the overhead that we discussed in the kernel here and have the application running in the user space directly pulling packets from the NIC. Now, this is great. It has some disadvantages. For example, now we are no longer having all the functions of the kernel, like removing the header of the Ethernet and then processing with the remaining of the stack. So essentially, we are just re-implementing all the logic in the application, the user space. But with that being said, now you are getting much, much better performance, right? You have this, what we call Polmo drivers, which is attached to your application. And the idea is that they will be constantly pulling packets from the NIC. You receive a batch of packet. Let's say you configure your burst to be 32, you pull 32 packets at a time or more. That's configurable. So what do we gain from that? Basically, we will avoid the overhead resulting from interrupts. Now you see here, there's DPDK mentioned. DPDK is this technology that would allow us to have kernel bypass. It's programmed in C. We're going to talk more about it, how it looks like in the next few slides. Now, DPDK stands for Data Plane Development Kit. It started as a project by Intel, but now it's open source, and most of the NICs today support DPDK. One additional thing that we can do with DPDK is running on multi-core CPUs. So in the hardware, right, in the NIC, in the network interface card, there's a module called receive side scaling, or RSS. This is implemented in hardware and ASIC, and the idea is that there's a hashing module that will be used to distribute packets to different physical queues. Now, those physical queues are going to be attached to some pipeline running the CPU core on DPDK. And the idea is that, well, if you have that same program you want to parallelize, you can run it on multiple core CPUs, and now they will be all extracting packets from the hardware and then doing processing at the same time. So now you are basically increasing the performance by leveraging this parallelism across the CPU cores. But also you can run different pipelines. You might say, well, I want this pipeline to do function A, this pipeline to do function B. That's also possible. So what are some performance numbers that we can expect? This is a simple layer 3 forwarding application implemented in DPDK. So the idea here is that you receive a packet, you parse up to layer 3, the IP header, you inspect the destination IP address, and then you match on it, you take an action, which is to forward out of the other port or the same port where it came from. As you can see here, we have 12 CPU cores. On the x-axis, we have the frame size. On the y-axis, we have the rate in million packets per second. So for this application, with 12 CPU cores, if you have 64 byte frame size, which is the worst case scenario, in real traffic, you would have a variety of packet sizes. But even like in the worst case scenario, with 12 CPU cores, we are able to achieve line rate, which is 148 million packets per second, 100 gigabits per second. Now, as we increase the frame size, you can see that we are still achieving the line rate. But of course, the number of packets we process per second decrease, just because now we are no longer sending as many packets to fill that 100 megabits per second or 100 gigabits per second, depending on what your link is. So this test was extracted from the performance report. This is for NVIDIA NICs Connect X6, which is available in Fabric. So you can basically do this experiment and reproduce it. And but there's also other reports from other vendors if you're interested in seeing like what do you get with other NICs, like from Intel or Marvell or any other vendor. Okay, so we talked about the added value of DPDK in terms of performance, but what about the challenges and disadvantages? The challenge with DPDK first is that it's a little bit complex and has a very large code base that get a little bit complex to get started with. So you'll have to be very good at C and know all the DPDK libraries, know exactly how how you pull packets from the NIC and then do the processing. Now, even if you know C, and even with all of that, C at the end is a language that is general purpose. It's not just designed for, programming data path or specifying packet processing. So you'll end up having to write extra lines of code if you want to do some very small, packet transformation. And if you want to implement a simple software switch, that would take you millions of lines of code. It's doable, it's already there, people have implemented it, but the code can get very large. And then adding new features to that code becomes even more complicated. I'm seeing a question in the chat. One quick question from Ganesh. Does DPK transport the entire packet or only the headers to CPU memory for processing? It transfers the entire packet, so you'll be able to access the payload. And we will see later on, there's an application that was done here by one of our students that did some deep packet inspection. So we're going to show you some of the results that we got there. Sure. And yes, if you have any question, please feel free to post them in the chat. I'll be able to hopefully answer them. And otherwise, we can wait till the end and answer, but just keep posting them. All right, so that takes us to P4. We were talking about the complexity of using a general purpose programming language like C for packet processing. So P4 is a language that is a domain-specific language for packet processing. The idea is that it's high level, so you define what are the protocols that you want to parse. These can be custom protocols or can be protocols based on some standards. And then you define how you want to process the packet. So the workflow is that you write a P4 program that can contain different functions like classification of packet, routing, access control list, whatever you want to implement there. Then you compile it using the P4 compiler that will generate a target-specific, or with a target-specific compiler backend, will generate a binary file, right? So if you are programming for a switch, for example, like one from Intel or Tofino, right? It has its own binary. If you are programming DPDK, that's a different target binary that you'll get. Software switch is different binary. So it depends on the backend that you are using. But the language itself, the constructs are the same. It's P4. And also it generates control plane contract, this P4 info that you see here, that can be consumed by a control plane application like Python or C, and then you'll be able to connect through this P4 runtime to the target device and then manipulate the data plane entries. For example, if you are doing forwarding, you want to push some of the forwarding rules, you can use this control channel, right, to push those. Now, keep in mind that this here is on CPU, so that's kind of the slow path. You shouldn't be sending all the packets between the control plane and data plane. But this is just used to manage the entries, the registers, counters, and other kind of data plane elements. And we're going to talk more about those. So when P4 started, it was just for switches. So the idea was to create this programmable switch that has this domain-specific language. And this here is called PISA, Protocol Independent Switch Architecture, which is an abstract model, basically, that defines how this, if you want to implement your own architecture for a certain device, you have to abide by, or roughly abide by this model, right? So first you have a programmable parser. You define the states. Let's say start by parsing Ethernet, then parse IPv4, then parse TCP, maybe parse even more, right? You can go DNS if you want to do like some custom parsing. Now, keep in mind, you cannot keep, complicating the program, especially when you deal with hardware devices like a switch, because there's physical limits, right, in the physical switch. So you cannot do a lot of deep parsing. You can do some to some extent, but you have to write an optimized code basically to be able to get there. And then you have multiple stages. These are match action stages where you have memory and then you have ALU units for execution. So this is basically the architecture, the model. Now, this is implemented with switches, and then now SmartNICs implement that. We're going to talk about that later today. And the idea is that you receive the packet, you parse, you specify what are the headers you are interested in using in your pipeline. Then you pass those to a series of match action tables. Those match action tables would do transformation on the packets. And then at the end, the deparser here would reassemble that packet out for transmission. So as a programmer, you'd have to write how you want to process your packets, and then what do you want to do with your packets? Match action, for example, doing the forwarding or counting how many packets for a certain flow, you name it. This is a simple code here. I'll just skip it because we're going to go more in details in the hands-on session. Now, why are we talking about P4 for CPU? As we said, it's a domain-specific language for packet processing, and it turned out that most of the processing options that you have for the switches are the same for end hosts. So for hosts, you still need to do this packet parsing and transformation of the packet, and then sending it whether to the other side of the NIC, right? Or sending it to a certain application on the host. So it's really the same. We can still follow the same model for the CPU. For reference, that switch implementation that we were saying that it will take millions of lines of code in C, that's only 5,000 lines in P4. You'll get the same functionality, right? Here, there are some other examples, and you can see how shorter the P4 code is for these different DDoS detection, basically, schemes. Now, what we would like to have is basically combining P4 and DPDK so that we can get the performance of DPDK, but at the same time, get the flexibility of using this domain-specific language, which is P4. And this is what this project P4-DPDK does. So you would write a P4 program, you compile using the DPDK backend. So this P4C is an open source compiler and the backend as well. That will generate a file, a specification file, just containing the instructions on how you are doing transformations on your packet and how you are parsing your packet. Now, DPDK has a pipeline library that has basically the idea of doing this match action. So you can create tables. In the table, you specify that you want to do this match on this key, and then you want to take this action. And basically, by leveraging this library, we'll be able to generate a C code that is representing what your original P4 code was about. And then after that, you would use the same process. So you'd compile using a C compiler, you get your shared object, now you can deploy it in your CPU. So we went all the way from just writing using P4, high-level domain-specific language, to running it on the CPU cores. What are some of the features supported? So we can do a lot of the features are already there. There are some that are newer. There are still some that are not quite ready. But for example, if you want to do like different match type, like exact matching, longest prefix match, LPM, wildcard matching, if you want to do registers, meters, counters, they are all supported. By the way, the blue here is just the new features supported, but all of these listed here are supported. You can do even recirculation. You can use software-based NICs, which we will be doing in this hands-on following, right? And many others, packet mirroring, you name it. Now, as I was saying, like P4 started really with switches, but there's this vision because of simplicity and how easy it is to get started with it. The idea is to try to write this whole stack of P4 code, right? From the user space, you write using P4-DPDK. Maybe if you want to do something in the kernel, you can use something like XDP. So P4-XDP is there. On the network interface card, you can use P4. Some of the high-end NICs, like the one that Paul was talking about, these DPUs, some of them support P4. Software switches like OVS, you can also use P4 on it. Physical switches P4. So you will see like you have an end-to-end path, all that is P4 programmable. And then you have this centralized controller that could be used with different control applications to control and manipulate those different targets that you would have. So that's the vision. It's not there yet. I mean, we don't have this end-to-end path, but we have all of these separate technologies there. So what we are focusing on in this workshop and this is this one here, the P4-DPDK, programming on the user space of the host. But at the end of the workshop, I'll also talk about the smart NICs. So I'm gonna highlight how can we use the NICs to offload some of the packet processing and data processing in general. All right, to conclude, so packet processing, the typical one on the server, has a lot of overheads due to context switching, memory copying, interrupts. This is okay for general type of workloads, but when you have higher speeds, like when we talk about 40 gig, 100 gig, we are not able anymore to get that 100 gig if you want to just follow the regular Linux processing stack, packet processing stack. So what is the alternative? We can bypass the kernel. By doing that, we lose some of the functions that the kernel provide, but if we can implement them in our DPDK application, you will basically get much better performance. You can use multiple CPU cores to parallelize, and the new effort is also to use now P4 instead of writing C code. So we will see today that you'll be able to write a pipeline, a DPDK pipeline. You get all the performance benefit of DPDK without having to write a single C code. It's just purely P4. And finally, the shared vision is to have this fully programmable stack, including switches, servers, and smart NICs. All right, so that's what I have for this session. Is there any question?
Quick question.
Yes.
So if I have some application that uses a lot of I/O operation, and will this DPDK improves that because there is a lot of read from I/O happening through the kernel calls?
Yes, definitely. To give you an idea, like what are some of the applications? We've seen a lot of applications on like cybersecurity. If you want to like get a bunch of packets and then do processing on them, you can use DPDK. Some of them are being used like for doing some relaying functionality. If there's a lot of packets, a lot of I/O, as you said, yes, it would improve. Now, the question is, how complex is your pipeline? Like, what are you doing with those packets? So it's at the end, if you create a very complex pipeline, you're still gonna have some increase in the latency. So the results that I showed with the L3 forwarding, this is simple L3 forwarding, right? But if you have, I don't know, maybe more complex operations, then you might need maybe more CPU cores to achieve that line rate. But in general, yes, it should increase the performance if you have a lot of I/O on your application.
Right.
Any other question?
Could you please touch on like limitation side of it too, if you don't mind?
Yes. So again, the limitation, if we're talking simply first about DPDK itself, in my opinion, I mean, based on what I've seen, it's mostly related to like the complexity of doing all those tasks that you want to combine in your application, right? Typically, if you want to like, let's say you are implementing a web server, you can like use TCP sockets and then just bind to a certain port and then wait for incoming, packets, and then you do all the other programming. So that's kind of the model that programmers are used to. But now if we want to say, well, we want to do a server that is, a DPDK based one. So now you can no longer say, well, I'm going to call this library to open a new socket and then wait for incoming packets. Why? Because you lost the functionalities of the kernel in terms of, sockets and parsing the packets and all of that. So what that means is that you as a programmer, you have to implement that part in the user space. Okay, so that's the DPDK aspect. I feel like that's the the main limitation. But there, I mean, with DPDK, you have, you write the program in C, so you can do a lot of, interesting stuff on your packets, right? On your payload, because you can import libraries and you can do pretty much a lot of the things that you would do in any language. Now, with P4-DPDK, the limitation itself is that even though, I mean, P4 is making all of it much easier to get started and having a pipeline up and running, but then you do not have the flexibility of a general purpose language. So you are still limited like type of match action processing. Now, this might be enough for most of the use case, but there are some use cases where you still want to do like some additional type of transformation on the packets, right? Additional processing that is not just doable with very simple operation. Like P4 itself does not support something like creating a loop or doing like multiplication divisions. You can approximate those with bit shifting, but you will not have the flexibility of what you would have in a general purpose programming language. But again, for most of the application, right, this is the fast path. So you shouldn't be doing that much computation at all, theoretically speaking. So for those, having this as represented in P4 might be more than enough. But again, it depends on the application.
Great, thanks.
Yeah. All right, I don't see any other questions. So now we will move to the next session here, which is a short 5-minute demo. So this is gonna be about how we at USC here, one of the research projects that we are doing, how can we classify encrypted traffic using P4-DPDK? And Amit here is a PhD student. He's just completing his first year now. So he's been working on using P4-DPDK to classify encrypted traffic. So I will let Amit share his screen and show us what he did. Amit, if you started, you're muted.
Yeah.
All right, go ahead.
So the topic which I have taken is like classification of encrypted traffic at line rate, and this has been implemented in P4-DPDK. And here we are going to discuss about the proposed system, what is the system, how we have built it. And if you see here in the diagram over here, we have like the control plane and the data plane. And mostly the control plane here is like we have taken one of the data sets for training the model, and using that training data set, and we are going to use the what do you call the model to classify whether the packets coming from the data from the network is like is it like a mobile application data set. It's like, are we classifying it as like a Discord packet, WhatsApp packet, or Teams packet, Signal packet, or a Messenger packet. So this is the data set which I have taken, and this data set is available publicly online. And if you see the control plane, this whole yellow block is being trained completely offline in a different server, where you see here it consists of a data set, and we train it using the random forest machine learning algorithm, and then we optimize it using the hypertuning parameters, and then we generate the rules which are being fed to the data plane for classifying the packets. And if you see this data plane here, it consists of two pipelines. One pipeline is used for extracting the features for each packet in a particular flow. So here, if you see, we calculate the flow ID based on the flow from which it is coming from using a phi tuple. And then we extract the features, like the features which we use to train this model are the minimum differential packet length, maximum differential packet length, minimum inter-arrival time, maximum inter-arrival time, and the total packet length. So these are the 5 features which we have trained the model, and this is the 5 features we are implementing in the data plane in P4-DPDK using P4-DPDK. And these whole program for extracting these features is written in P4, and then using this PNA architecture, and then we update this flow metrics using the registers. And then we pass it through the second pipeline through the ring buffer. And in the second pipeline, we use the rules which are generated from the offline model, and we match, if there's a match with those values from the extracted features, then it is classifying the packet. So we classify the packet and we get the class results as shown over here in this decision trees. And then the final classification result is based on the majority voting, which each decision tree is generating the class. I mean, like whatever classes are generated from this decision trees, the majority of this class number, whichever is being highlighted the most, is taken as the final class, and it is stored in a register over here. And this is how we are going to classify the packet. And in the next diagram, we show how this has been tested. We have used Fabric test bed over here, and we have 3 different servers. And first server is like you're generating the background traffic. And the second server is like we are generating the encrypted traffic. And the third server, which is used to build the pipeline as shown in the proposed system. And we'll be having this background traffic running at the from the server 1, and it keeps sending the package to the server 2, and the encrypted traffic sends the actual dataset traffic to the server 2 for classification. And both of them are using ConnectX 6 NICs with 100 gig throughput. And you can see in the next slide, which we show the demo here, and how it is being classifying the packet. And here you can see we have 2 servers, server 2 and server 3. Please note the server 1, we have the background traffic being running. And now in the server 2, we build the pipeline. And in the server 3, this is where we are replaying the traffic, the encrypted traffic. And if you see this comment here, this is how we build the pipeline using the CLI script. And you can see there are 2 pipelines being run, which are shown from the proposed system, the pipeline 1 and the pipeline 2. The pipeline 1, which is responsible for the feature extraction, and the pipeline 2, which is responsible for classifying the packet. And both the pipelines are built as shown over here, the list of pipelines. And the first pipeline is responsible for the feature extraction, and second for the classification. And you can see here we can access the registers using the control plane and using this telnet. Now in the server 3, we are replaying the traffic, and you can see we have replayed the traffic using TCP replay, and we have one flow shown over here, that is Discord. Since we are replaying a Discord traffic over here, and we have to get a class 1, and the pipeline should classify it as a class 1. And we have to see, we are going to see if it is classifying it as class 1 or not. And we see here in the first command, we get the flow index using this flow index register, and we see we got it in hexadecimal format. And then using the flow index as an indexing to the register, we get the class 1. So it is clearly classifying the Discord flow as class 1. Now we are replaying the Teams flow, which should classify as class 6. And we see the same thing being shown over here as a class 6. And this we keep running it for different applications. Since we have in a data set of 6 applications, it should give 6 classes. For time being, we are just showing 3 here, but it is classifying all the 6 packets, all the 6 applications. And that's the demo.
All right, thank you, Amit.
Thank you.
So one of the things also to add here is that your pipeline will be able to process 100 gigabits per second at the same time while classifying those, right?
Yes.
So the background traffic, if you go back to slide 3, there is basically 100 gig of traffic being generated.
Yeah.
Okay, so yeah, this was just like a short demo just to show you what you can do with the technology that we'll be talking about today. So we will do the labs. We're not gonna go into all the technicalities of training a model and what Amit is showing, but we're just gonna give the basics, and soon enough we're gonna have a library, a bunch of labs where one of them would be running an application like this one, and we will see we have other demos later on. But essentially, by doing the lab, you will get the foundation so that you can experiment and run a system like this. And if you're worried about, well, I don't have a high-end NIC or 100 gig links, as Paul was saying, you can request access and now become part of Fabric. You don't have to run your whole node in your campus. All you have to do is just have an account there. And then you will get a Jupyter Hub notebook, so it's a programmatic interface. You will be able to get there basically the resources and then run these experiments at high rates. And there is, later on, we're going to show you an example of one of the labs that we developed over Fabric. So if you want to run it there, all you have to do is just follow the steps, and from deploying the topology all the way to getting this 100 gig of packet processing. All right, thank you, Amit.
Yeah. Thanks.
So back to the agenda. So we finished a little bit earlier, 2 minutes earlier. First, is there any question before we go to a 10-minute break?
Yeah, one question I had, Eli. So this was a very nice presentation. Do we have any confusion matrix generated for the classification? Are we seeing?
Yes. Actually, you can go through the website link provided by Eli, and there's actually one of the PDF, one of the presentations, and it has the confusion matrix results over there.
So basically what, and Ali, if you can please add that presentation to the list of resources at the end of the workshop here at the bottom of the page. But so here we have a presentation, trying to see where it is.
It's in
oh, it's a referee presentation. Okay. So see here.
Yeah,
right?
Something like WhatsApp text chat and some other text chat will have very similar characteristics, right? So that's what I was looking for.
Yeah, that's a great observation. So here we have this, the confusion matrix. Amit, what was class number 5? Do you remember?
It's a messenger class. So class number 2 is WhatsApp class.
Okay. So yeah, you can see here.
The class 1 is Discord, class 2 represents WhatsApp, class 3 represents Signal, class 4 represents Messenger, class 5 represents Telegram, class 6 represents the Teams. So these are the 6 classes provided by the dataset. And this was the offline training accuracy when we trained it offline, and these are the results for it. And you can see most of them are more than 90.
Yeah, there's this class here, class number 4, though, has some misclassification, right?
Yeah.
So there's some confusion between class 4 and 6, it seems, right?
Yes.
And what was class 4 and 6 again?
6 is Teams.
Okay.
And 4 is Telegram.
Okay. Yeah, and that model probably can be also enhanced, right? Because the plan is now to add even more data sets and more
yes,
different types of applications. So this model should be revisited for sure. But that's the preliminary results that that Amit has.
Yeah, that's interesting. Thank you.
Thank you, Ganesh. Any other question? All right, so let's take a 10-minute break. We will be back at 2:10 p.m. Eastern Time. And I will just update here. Meanwhile, if you have any question, please feel free to post them in the chat. We will answer them when we come back. Thank you. All right, welcome back, everyone. So the next session for today is gonna be a hands-on session lab. So this is an introductory lab on P4 and DPDK, just to get you started with how does the code look like and how you can compile and deploy it to the pipeline. And the presenter is Sergio Elizalde. So Sergio is a PhD student here at USC. He's been working on different technologies related to packet acceleration, including SmartNICs, DPUs, DPDK, and others. So Sergio, are you ready?
Yes, I'm ready. Thank you for the presentation. My name is Sergio Elizalde. As Lee mentioned, I'm a second-year PhD student. And today I will guide you through this first lab in the P4-DPDK lab series. So let me share my screen to get started. Okay, so first I will introduce the lab using a presentation that's available in the workshop page. So let's open, and we're going to go through this presentation. All right. So before starting with the lab number 1, I want to show the overview of the whole lab library that we have about P4-DPDK. I will say that this is a lab library that will introduce you to P4-DPDK. This is a starter pack for you to learn about P4-DPDK, how to deploy pipelines. Also, we have detailed explanation about the PNA architecture, that is the portable NIC architecture. Very important also is the lab 4 and 5 that describe the match action tables are a key component of P4, and more, let's say, advanced topic of populating these tables in runtime, and also packet checks on recalculation and packet deparsing. So this is the overview of this lab. Also, before starting the lab, let's discuss some points that Eli already mentioned. First, we have, for example, the DPDK pipeline model that we are going to configure today. It has 3 key elements: the input ports, the tables, and the output ports. So the input port are these RX ports that we have. We receive packets on those. Then we process these packets using tables in a match action manner. So we can match on different keys. In this case, in the example, we have, for example, flow number. We can also match in, let's say, IP addresses, even in packets size, etc. And at the end, we have the transmitting ports or the output ports. So we are going to configure this today in lab 1. Also, we are going to go over the workflow that we are going to use to configure the P4-DPDK pipeline. We have a P4 code that is already provided in this lab. We are not going to write this code today. We will have a simple forwarding application in P4, and we are going to compile this P4 code with the P4C compiler, selecting the target DPDK. And we are going to continue this process by, again, configuring the DPDK pipeline library. We are going to compile the docspec file into a C file. And finally, we are going to compile this C file into a shared object. So this is the whole path that we are going to go step by step in this lab today to deploy our pipeline. So let's take a closer look at what are these files. So for example, here at the left, we have the P4 code. In this case, we have an apply block that is basically forwarding a simple forwarding application. For example, we have an input port. If the input port is 0, we are going to send to port 1, and vice versa. If we have an input port of 1, we are going to set the packet to port 0. So this is the logic, and at right, we can see this .spec file generated after compiling this code with the P4C compiler. So here we have different instructions, as Dr. Eli mentioned. For example, we have extract the header, the Ethernet header, and other instructions that are similar to what we can find in an assembly code. For example, jump on equal, jump, and more specific ones that are, for example, emit, that is packet emit or emit a packet, and transmit. So this is how it looks, the .spec file. And now let's discuss what are the objectives of the lab and what is the topology. So in the topology, we will have 2 namespaces, H1 and H2. We are going to attach two links or 1 link per namespaces, that is D.0 and D.1. And these links also will be attached to the P4-DPDK pipeline. And this pipeline, what we'll do is we'll forward the packets that are sent by the host H1 to H2. So the objectives are to implement a DPDK pipeline, building and running the application. Also building this network topology, we are going to build from scratch this topology, and testing and verifying the P4 program. We are going to run a ping test to verify that the pipeline is forwarding the packets. So now let's get started by accessing the platform that is available in this presentation. You can click on this link and you will be redirected to our platform that is NetLab. And you have to use your email address that with the one that you registered with. And if you are a new attendee, this is your first day, you will need to use this temporary password. Otherwise, you have to use the one that you configured before. So let's do this. I will now exit this presentation and open NetLab. So from here, we are going to enter in the platform. In my case, I will use a test user. I guess it's test user 2. Let me just check my credentials. And the password for me is NSF. That's 2025. All right. So let's log in. If it's the first time you are logging in this platform, it will ask you to reset your password or change your password. I will do it right away. And now also you will be asked for an email address. In my case, I will use my Gmail address. And also the time zone that we need to configure in this case. We are using Eastern time. And this is okay. So let's submit. And now we have to, we are going to be in this page. So we are in the NetLabs. I will wait a few seconds here until all of you configure your account and enter in this page. From here, we are going to schedule a lab reservation in this platform. This is a virtual environment, but also some of the labs, you can also have access to real hardware. So this is a good platform to conduct these labs. So if you have any issue logging in this platform, you can type in the chat and we can reset your password or help you to access to this platform. So I will wait a few seconds and then we can start by scheduling the lab reservation. Let me check if I can see in the chat here. I don't think so. All right. So I will continue by scheduling the lab reservation. We have to click on new lab reservation, scheduled lab for myself. Now here we are going to see what are the different contents that the different classes. And here we are going to click on the P4-DPDK labs. And here we have all the labs that we have in this lab library. We are going to start with this one today, lab 1, introduction to P4-DPDK. So let's click on this. And here we are in the pod scheduler. And we can see that there are already some reservations. To navigate to other pods that are available, we have to click on the right arrow here and find a spot that is available. So for example, here we have to be careful and click on over this red line to reserve a pod in the current time. Make sure to click over this red line. Otherwise, you will not have access right now to the pod. And we are going to schedule for about 1 hour. Let's say, okay, 1 hour and a half is fine. And we have to click on submit and we are good to go. Now we press OK and we will see here our lab or pod that is available to use. We have to press on the enter lab in order to access the environment. But before also I will wait a little bit so everyone can reserve the pod and can have this reservation to enter. So I will wait so all of you are following this in real time. After you see this, you are good to go because you have the lab reservation and it's up and running. And we can press the button that is Enter Lab. And with this button, we are going to enter in the virtual environment. It will initialize the pod. It will take a few seconds. So here we see that we have 4 tabs. And mainly, we are going to use the content and the client. So in the content, you will find the lab manual that describes all the steps that we need to do this lab. This is a very comprehensive manual, straightforward. You just need to follow step by step and you will be able to finish the lab. To work on this on one screen that I'm going to work now, I will undock this content. So let's click on the down arrow here and undock this document. And we are going to put side by side. So let's put at the left. So we have the manual here, and here we can put the client. So now let's do the same for the client. That is the VM, the virtual machine that we are going to use. We have to click in the down arrow and do the undock. All right. So now we are good to go here. Let's put it on the right side. Cancel. And one thing here, so you can see it better, I will click again in the down arrow, and I will resize the displays just to use the whole screen. All right. So here we can start the lab. So I will wait a few seconds so you can also load this page and prepare your environment to work with this lab. To this lab that is the introduction to P4-DPDK. This manual, we are going to go over it now. First, you have the table of contents, that you have all the contents in one page. And we are going to start with the overview. We already mentioned this in the presentation. We have here the overview of this lab that is introducing the P4 and DPDK framework. Also, very important is the lab settings and the credentials. Every time we are asked for a password, we are going to type password when it's needed. This is the credential for this VM specifically. And then we'll start with the introduction. So here we have basically the introduction and the background. All these concepts were already explained by Dr. Eli. Here we have why we need P4, why also we need DPDK to accelerate packet processing, how this works together, and so on. So we have here all the details that we were explaining in the different presentations today. Also, we have a detailed explanation of the memory allocation in DPDK, how these different elements help to optimize the packet process. All right, and we finally have the lab topology that also was included in the presentations. And we are going to start the lab, doing the lab in the section number 3, that is implementing the P4 DPDK pipeline. Okay, so we are going to start directly here, section number 3. So the first thing that we need to do is to open our code editor. To do so, we need to open a new terminal, the step number 1. Let's open a new terminal. And we need to type code and the path to the folder that we are going to work with. So in this case, it's P4-DPDK labs/lab1. So this will open. We have to wait a little bit. We'll open the lab manual.
Yes, Sergio, make sure you remove the slash in front because it will take the root basically.
All right. It's like this. Lab 1. All right. Thank you, Dr. Eli. So now we loaded the path, the folder in which we have different files already there provided in the lab. So the first thing that we need to do, let's click on the lab1.p4. This is the program that we are going to compile. And here we have a full program that have everything that we need to process packets, like, for example, the headers. We have the Ethernet headers, IPv4 and TCP headers. And then we have other part of the PNA architecture, such as the pre-control, the main parser, and so on. And at the bottom, we have the main control implementation, that is the logic of the program. Let me just close this, and I think so you can see everything. And here is the logic of the program. This code is already provided. We are not going to write any P4 code here, but what we are going to do in the section number 3.2 is to compile the program. So for compiling the program, let's click on the terminal tab and open a new terminal. And we are going to type this command, this command in the terminal. So let's start by issue the command P4-DPDK. This is the compiler targeting a DPDK target. And then we have to provide, secondly, what is the architecture of this P4-DPDK. We have two options here. We are going to use the PNA architecture. If we notice, we just saw that in the includes of this P4 program, we were including the DPDK PNA architecture. So let's do this by typing architecture is PNA. Then we have to provide the input file that is the lab1.p4. This is a P4 file. And we are going to output this, the output of this compilation will be in a file that is lab1.spec. So now we are generating the spec file that we saw in the workflow. So the input is the P4 code, and the output is the lab1.spec. All right, so I will open again Explorer so we can see that after we compile this code, we are generating the lab1.spec file. And this is the one that we show also in the presentation. We have all the struct for the headers, and then we have the different instructions here. All right, so we just compiled the P4 code. We have the spec file. So we are done with this part of the lab. So let's continue scrolling down. The next step that we need to do is preparing the P4-DPDK CLI script, the command line interface script. So to do this, now we are going to move to the file that is lab1.cli, that is also here in the folder. And here we have an empty file, so we need to type here. We are going to configure this. And we have some hints. So for example, the first line says, generate the pipeline code and build shared objects. So here, we need to do so. We need to start building the application and continue with the workflow that we were showing before. All right. So the next step, if we remember in the workflow, we have the spec file, but now we need to create a C file. Okay. So to do so, we are going to type this first line, that is the pipeline code generation, code gen, and we are going to provide the path to the spec file that we just generated. So the path is home admin P4-DPDK labs /lab1. This is the folder, and now we are going to specify the file that is .spec. All right, let me just check that I don't have any typo. Okay, so this is the input file for the code gen, the spec file, and we are going to generate a temporary file that will be the C code. So this will be under the temp file and the lab1.c. All right. Let me just close this again so you can see the whole line. Okay, there you go. So we just create this C file from the spec file. So we are in the, let's say, the second part of the workflow that we just saw. We compile P4 to spec file, and now the spec file is compiled to the .c, that is the C file. And then the last step that if we remember this workflow, is to compile the C code to a shared object file. Okay, so this is the second line that we have here. Pipeline lib build. This is the command for compiling the temporary file that we just created in the previous line to another temporary file that will be lab1.shared object. Okay, so with this, we just finished this workflow that we were looking at before. To starting from the P4 code in the Visual Studio Code, we compiled it to a spec file, and here we are compiling again the spec file to a C code, and finally the C code to a shared object. Okay, so we are done with this workflow that we mentioned, and now we have to start configuring what is the DPDK pipeline model that we remember. We have inputs ports, we have different queues and transmitting ports also. So now the next step is started with doing that is listing the DPDK devices. All right, so let's scroll down, and step number 3 is listing these devices. First, we are going to configure or declare the memory pool that we are going to use to allocate packets. This is the first thing. So to do so, we have to use the command mempool. This is the function that will create a memory pool to allocate packets. We have to provide the name that is, in this case, mempool 0. This is the ID of the mempool or the name of the mempool. Then we have the metadata associated with the packets. If we are going to allocate some memory for information related to the packet, it can be, for example, for context, the ingress, egress port, also timestamp. In this case, this metadata or meta will be 0 in this data structure of the mempool. Then we continue with the packet size, the maximum packet size. In this case, we are configuring 9,128 the size of the packet. This allows you to, for example, have jumbo packets because we are talking about in bytes here. So it's around 9,000, it's 9K bytes. Then we have the pool that it tells you in bytes what is the size of the total pool that we will have. In this case, we are declaring 32K bytes. And also we need to set here the cache. So the portion of this total pool that is 32K, what is the portion that will be allocated in the CPU cache? Okay, so in this case, the cache we are setting to 256. And finally, we have to provide the NUMA node ID, that is in this case is 0. So now we finish the mempool configuration. This is, I want to repeat that this is for allocating the packets. The packets will be allocated in a mempool, a memory pool, and we just configure what is the structure of this mempool. Okay, so the next step, and now we are going to define the Ethernet devices. All right, so let's define the Ethernet device. The first one is the net tab 0. This is the first Ethernet device. We need to provide the size or how many queues, receiving queues we have. So this is the receiving queue. We are going to have one receiving queue and also the size. And in this case, we are configuring the size as 128, all right? Which is the mempool that we are going to use. In this case, is the one that we just created, the mempool 0. And also we have to do the same for the transmitting queues. We will have one transmitting queue and the size is 512. And finally, we are going to enable one configuration to on, that is the promiscuous on. This allows you to receive all the packets that are arriving to your NIC, no matter if the hardware address, for example, the MAC address, is corresponds to your NIC. All right, so we are processing all the packets that are coming to the NIC. Okay, so we are done with this. We have to repeat the exact same thing with the other NetTab 1. It will have one receiving queue with 128, size of 128. It will use the same mempool. Similarly, for the transmitting queues, it will be one transmitting queue and 512 size. And finally, the promiscuous also will be on. Okay. So now we finished customizing this parameter. Now, this is very important because you can change this. This is not a fixed or arbitrary value. Like these are arbitrary values, you can fix it. It's not like this is a you have to be the same every time for every application. This is, you can tune it. And this, all of these parameters are related to DPDK. Okay. And so let's continue. We just finished the listing of DPDK devices, and now we are moving into listing the pipelines. And in this case, we have only one pipeline. We are going to use one pipeline, and we need to type this command that is here. So let's write pipeline. The name of the pipeline is pipeline 0. Now we are going to use the build lib. This is the one that will basically compile the shared object again into the binary to run this code in a CPU. So we have the shared object under the temp file, temporary folder lab1 .so. And next to it, we have to declare what is the input-output configuration for this pipeline. If you remember the DPDK pipeline model, we have the logic in the middle, like the match action tables, and we have the different input-output ports. So now we are going to append what is the file that contains this information. So let's type home admin P4-DPDK labs lab number 1, and finally the file. This eth-dev.io we are going to configure in the next steps. This file will basically define what are the inputs ports and the output ports of this pipeline that we are just creating here, the pipeline 0. Okay, and finally we have to specify what is the NUMA node ID, that in this case is 0. Okay, so we are almost there. We just need now to map the pipelines that we just created to the CPU threads. So at the end, we want to run in the CPU threads or CPU cores. Okay, so to do so, let's type this last command, that is pipeline, the name of the pipeline 0, and we're going to enable this pipeline in thread number 1. Okay, so after you finish this configuration, we need to save the file, Control S, and now this file is ready. Just make sure, of course, don't have any typo. Let me just check if I have any typo, because this, of course, will bring problems when we are running this pipeline at the end. So yes, this is the CLI script. So we just finished the CLI script.
Yeah, Sergio, one comment here. So for everyone, like there has been a lot of like parameters, right? So that's fine, because most of the time this file is fixed. So for example, if you are trying to create a new type of logic, most of the time what you'll end up doing is reusing one of those files. You just simply modify the path to your P4 spec file, right? The generated file. Yeah. And that's it, right? Now, you might say, well, I want to optimize my program. Let me play with the queue sizes, or let me play with multiple pipelines instead of a single pipeline. But really, you don't have to memorize all of this. So this is just like, if you're feeling that there's a lot of parameters, most of these are DPDK specific, like, you know, the mempool, the packet, the cache, all of those are really just DPDK. And it's nice to have them here just because you'll be able to tune your DPDK application. But for development, like if you're testing, the first thing you have to do is just, you don't have to worry about all of this. Later on, when you try to do like performance testing with higher rates, and you see that I can further tune my application, I can go ahead and start playing with this file. I just wanted to mention that because all the programming is not happening here. This is just to load your program, which is in the P4 code that Sergio showed before this step.
Exactly, yes, exactly. So yes, basically we just want to change the P4 code, or even if you can also only use the .spec file here, right? Okay, so there are different ways, but the thing is, yeah, this most of the time is fixed. Yeah, you can add more pipelines, for example. You can do some tuning here, or add more queues to your program. I mean, you can change this, but most of the times it's just a matter of using the same file and changing the path. Thanks, Eli. So now we just finished with this. I guess I don't have any typos. I have a question. Okay, let me check. How can I? Oh, okay. Somebody is raising the hand, so you can open. Okay, yeah.
Yeah,
Okay.
so question is there is a cache mentioned here in terms of memory pool and all. Does that cache also rely on what's the cache in switch that, you know, yesterday, day before yesterday, we mentioned in the last lab that there is a cache in the switch side and the router sides. Does it affect in this cache, or it's the same, or it's a different?
I think it's a different. When we are talking about DPDK, we are talking about CPU architecture. Yeah, you can have, for example, running a code for a router in a CPU, but this cache is more related to the architecture of a CPU, in which we have memories that is allocated in the RAM memory, and then we have the cache that is close your CPU core. Okay, so this is the cache related to this core that we are going to use later. That answer the questions or not?
Yes, thanks.
Yeah,
Alright.
the cache, yeah, from the 2 days before it, we were calling it like buffer, right? Buffer size. That's like for the router, like how much packets you can hold momentarily into the router, right? As when you have congestion. This is different than that. So it's not about how much packet you can hold in the memory, right?
Okay.
This is just
Yeah.
like, yeah, it's just here, like you are caching some entries to do faster lookup so that you can access packets faster, basically.
Great. Thanks.
Exactly, yes, exactly. That's the answer. Thank you, Ali. And yes, so now we can move to the section 3.4, that is preparing the IO script. That is the one that we just invoke here, the ETH dev IO. So this is not configured yet. Now we are going to configure to provide the input port and the output port for the pipeline that we just created. So let's navigate again to this file that is the ethdev.io. And here we need to type first the input ports. So let's start with port in. This is the command. And then we have ID 0. The ETH device is the one that we created in the CLI, that is net tab. Well, we have here net tab 0. The RSQ, here we are configuring the RSQ ID. And the ID of the receiving queues start by 0. So we are going to use QID 0. And also we have here the burst size. So the burst size is a parameter in the PDK that tells you how much packet you are processing at once. For this lab, for demonstration purposes, we are using a per packet basis. But if you are looking for performance, you need to increase this. So this is also a DPDK parameter here. So let's repeat the same for the second port. So it's port in 1, ETH dev net tab 1 in this case. And the receiving QID is also 0, and with the same burst as 1. All right. So here we have the 2 input ports for the pipeline. All right. Next, we need to do the same configuration for the output ports. Okay, so let's do port. In this case, it's port out. Scroll down a little bit to see the exact command. Here in the step number 3, we have port out 0, the first port. The ETH device is net tab 0. And in this case, we are configuring the transmitting QID, that is 0, with a burst size also of 1. Okay. And next one, again, similarly, we configure the second interface, that is net tab 1. You just click here, and the transmitting Q 0 with a burst size of 1. All right. So here, this is our final file for the Ethernet device.io. So we have here.
So one more comment. What you are seeing here with those net tab 0 and net tab 1, right? And also Sergio showed that in the CLI file, right? These are virtual interfaces. They are what we call tap interfaces in Linux. So it's just like a software-based NIC. Now, if you are doing DPDK with actual hardware NICs, instead of writing net tab 0 or net tab 1, you have to write the PCI address of your NIC. For example, 0000:007 or whatever the address is. You have to write all of that there. That's how you differentiate between a software NIC, which we are using here just for testing, for learning. But if you want performance, you need to use the hardware NIC, right? And you can get that address if you write LSPCI. It will show you all the PCI devices in your system. And then based on the name, like for example, Connect X5 or Intel IPU, whatever it is, you can go and get that PCI address and use it here.
Exactly, yes. So basically we have to change this if we are using if we are using a real hardware, for example. And also, of course, tune your parameters accordingly. Typically, but the default birth size of DPDK is 32. All right, so.
There's a question, Sergio, again from Trupesh.
Yes.
So if I have to have hard-coded IP addresses there, how do I do it if there is an HPC facilities where I'm running my application, and it's a Slum-based application? Do I have to dynamically update this IPs all the time?
So just to be clear, what you write here is not the IP address, it's the PCI address. So if you, Sergio, if you go to the terminal and just type here ls PCI. Okay, so you see here, like these are different PCI address. You can see pretty much a bunch of them. Now here we're using VMware Stack, so you can see a lot of the bridges there. But in your server, let's say you have a NIC that you plugged into that server. You should see there, based on the vendor, let's say Mellanox or NVIDIA now, or Intel, or whatever it is, you will see the first part is the PCI address. Like what Sergio is pointing at, that's 0200.0, that's the PCI address. So this is what you have to write in your .io file and CLI file. It's not the IP like IPv4 or IPv6. So all the IP addressing, that's separate, that's part of the P4 code and how you are populating your P4 tables. So in a HPC setting where, you know, you might be changing the logic from one server to another, that's totally fine. You can update those parameters at runtime.
Got it, thanks.
Exactly, okay. Yes, so now we are done with the ETH-IO. So let's continue scrolling with the lab manual. And the step 3.5, the section 3.5 is about running the P4-DPDK pipeline. So now we finish the configuration of the P4-DPDK pipeline and we can run this program, okay? So to do so, let's go back again to the terminal. Just let me clean this terminal and do sudo, enter in super user mode, sudo su. The password here is password. And from here, we are going first, before running the application, we need to allocate the HUD pages, all right? In this case, we are going to allocate 1024 HUD pages. These are basically the memory to store the packets in the RAM. So to do this, let's type this command that is this kernel, the HUD pages, and we are configuring the HUD pages of size 2 megabytes or 2048 kilobytes. And then we need to change the parameter that is number of HUD pages. All right. Okay, so this is the command. With this, we are reserving the memory to allocate packets in the system. Perfect. And now we can run the pipeline. To do this, first navigate or go to the DPDK folder. That is cd DPDK. Inside this folder, we are going to run this command that will run the pipeline at the end. Okay, so let's start by writing examples. We are now selecting the pipeline code in DPDK. The pipeline is an application in DPDK. Then we need to specify the number of cores. To do this, we are going to provide a mask, selecting the cores that we want to use for this pipeline. Okay, so in this case, we have in hexadecimal 03. This is use 2 cores because 3 in binary is 1, 1. Okay, so we are selecting, let's say, thread number 0 and thread number 1. And the pipeline, if you remember in the CLI script, is running on the thread number 1. And the thread number 0 is used for management purposes. We will see later that we are going to, for example, telnet to this pipeline. So we are using 2 cores, but only 1 for running the pipeline. And yeah, so this is the first flag that we have to enable, the cores. And then we have to list the devices, the virtual devices. That the first one is net.0. The MAC address is, in this case, we are going to set to 1. Like this. And we have to repeat the same for the second interface. That is net tab 1. All right. So net tab 1 like this. And then also we are going to configure the MAC addresses to 2, basically. Like this, okay? And finally, we need to provide the CLI script. This is the file that will contains all the configuration for the pipeline. We'll launch the pipeline in the thread that we want, okay? So let's provide this like home. This is admin. This is the P4-DPDK labs, the lab number 1, and then lab1.cli. And we need to press enter here. All right, so if you remember, so here first we have some DPDK specific logs until here, like how many CPU cores, NUMA nodes, etc. And then starting from here, we have our CLI script that we just wrote. So we have all the things that we just wrote there, and we don't have any errors here. If for some reason you have some errors here, you have to go back again and check that there is no typo compared with the manual. And now we are running this file, but I think here for some reason I think it's not running here my pipeline because it's missing. It is? Okay, perfect. So let's continue then. Now we just have to keep this there, and now we are going to inspect what are the interfaces to see how we will have to configure now the topology for our experiment. That is a ping test, okay? So first click on this at the corner, at the left top corner to open a new terminal, and let's issue if config to see what are the different devices. So in the Linux kernel, we have these two, DTAP0 and DTAP1. So these are the ones that we are going to use to create our network namespaces. Then now we need to telnet to this pipeline. So to do this, we are going to issue this command, telnet 0008086. And now we are inside the pipeline command line. And from here also we can inspect what are the ETA devices associated with our P4-DPDK pipeline. So let's do ETA dev show. And we are going to see here that these are the Ethernet devices attached to our pipeline. All right, so NetApp 0 and NetApp 1. Perfect. To go to quick from this pipeline, first we need to press Ctrl plus the closing square brackets. And after that, we need to type the quit command. Now we are out the pipeline, and we can start by creating our topology. Let's again enter in super user mode. All right, okay. And then we just need to create the topology for this experiment. So first we need to create two network namespaces. That is H1 and similarly H2. Okay, so these are the two network namespaces. Then we need to attach the virtual interfaces, DTAP0 and DTAP1 to these namespaces. Okay, so to do this is IP link set DTAP0 will be in the namespace H1. Okay, similarly, we will do DTAP1 for the network namespace H2. Okay, so these two steps, that are step number 1 and step number 2 under the 4.2 section. Next, we need to set up these interfaces. So let's execute this remotely to the network namespace H1. The command is IP link set dep. We have to select the interface that is DTAP0 to up. And similarly, we need to do the same for the other interface. So we execute in H2 namespace the IP link set dep DTAP1 up. Okay. Now we are just setting up both interfaces. We are almost there. Now we need to configure the IP addresses in order to do a ping test. So again, we will execute in H1 an ifconfig command We are choosing the DTAP 0 interface. And the IP address in this case is 192.168.10.1/24. And then we have to do the same for the network namespace H2. The interface is DTAP1, and the IP address is 192.168.10.2 in this case, /24. All right. So let's press enter here, and we assign the IP addresses. And the last thing we need to do in order to do a ping test is to, these are the same steps that we just covered, to assign or to populate the ARP tables. These are the hardware MAC addresses. Okay, so let's do this again. IP netns execute in H1, the network namespace. The command is ARP. The host is 192.168.10.2, and the MAC address for this host is all zeros and 02. This is H2. So we are populating the table for ARP in H1. And now we need to do the same for populating the ARP table for H2. In this case, the host is 192.168.10.1, that is H1, and the MAC address is 000001. All right, so now we configure our topology, the network namespaces, and let's now run a ping command. So we are going to execute from H1 a ping command. So this is the remote execution, the ping command to the host 2 IP address is 192.168.10.2 and 4. So we are sending 4 packets here. All right. So after we send 4 packets, we can go back to the previous terminal tab, and here we can see some logs. So these logs are related to the processing of these packets. There are packets coming to one input port, then transmitting to the other port, and so on. To close this or to terminate your pipeline application, you press Ctrl+C here, and now it's closed. And this concludes the lab number 1. So you can now end your reservation if you want. All right, so if you have any question, I will be more than happy to answer.
Thank you, Sergio. One additional comment. So what Sergio did regarding the ARP configuration, we just did that here because the P4 program is not written in a way that it understands like, ARP and does MAC learning and all the other stuff. Now, this shows like one of the downsides of having to write your own packet processing. There are some features that you would need to implement them yourself. In this case, because the P4 program is very simple, so we had to do that manually, right? Now, of course, in reality, you can just have that block of code, take it from somewhere, you put it in your program, and it works. But if you don't have it, then your switch is not processing your ARP packet, because your parser might be written in a way that, well, if it's not up to the IP header or TCP or whatever, just drop the packet. Okay, so that's why we hard-coded these values here. Now, again, I would just want to reiterate that all this lab is just to show you like how to get it up and running like from scratch. So what Sergio showed, you can run it on your own device, and because you're using virtual NICs here, you can do it even on your laptop. That would work. Now, when you start doing more advanced applications, like what we're gonna see in the second hands-on session, all these steps, you can put them in one script, in a single script, and then execute them once, so that we don't have like to retype all of those. But it's good to see them so that if you wanna recreate that scenario at home in your laptop or any device, you can still do that and understand all the components. All right. Is there any question before we move to the next session? All right, I don't see any. So thank you, Sergio.
Thanks, Ali. Thanks to everyone.
All right, so next in our agenda, we have, I will just spend a few minutes talking about what are some other labs that we have for P4-DPDK, but then I will hand it to Samia to discuss one application she's working on for her PhD, which is detecting and mitigating distributed denial of service attacks using P4-DPDK. So Samia is a PhD student, second year here at USC, and she's been working on various DPDK-based applications. So what are the labs available that we just developed here? So what Sergio was showing is lab 1. Now you have the other labs here up to lab 7. These should give you the building blocks, the basics to get up and running with having a very simple pipeline. So lab 2 is about understanding the PNA architecture. So this means how can we connect the parser to the match action blocks to the deparser? What are the components in each? And then we will go deep into each one of those, right? So for example, for the first part, the parser, there's a lab that will show you in detail how you write the custom headers that you want to parse, and then how you jump from one state to another while you do the parsing. Then match action tables. So how can you write, for example, like a table that would match on the destination IP address and then take an action, like forward it out of a certain port? Or how can you do something like, I want to implement like layer 3 kind of routing, right? So you would do decrement of the TTL, and then you swap the MAC addresses, stuff like that. So it's all described here. Then those tables have to have entries. So how can you populate them at runtime? And that's similar to what Sergio was showing in the telnet interface, where you access the control plane of that pipeline. Then you can start adding rules to specify, like, what are the rules that you want to push to your tables. And finally, how you calculate checksum and you parse you deparse the packet for transmission. So that's the first library. The second library will add a few more labs to it. These are related mostly to cybersecurity. So one of them is how can we calculate the inter-arrival time of packets? So you have a certain flow and you want to understand or analyze the distribution of the inter-packet gap. Okay, so for that flow, we have 2 packets. What is the time difference between the 2 packets? This is very useful for a lot of applications. Earlier today, Amit was mentioning his machine learning model. So that, for example, that was used as one of the features for that. And you can use it for machine learning and cybersecurity, for instance. Next, we have like a simple DDoS attack here, synflood, and how you can start dropping rates probabilistically. So you can say something like, I want to drop 10% or 20% of the packets. How can you identify heavy hitters? And how can you optimize the resources in terms of storage using sketching algorithm like count min sketch? And how can you implement a stateful firewall or stateful packet filter? So this way you can associate the returning traffic from the outgoing traffic. So these are labs available, and you already have access to those over NetLab. So if you want to run those later on. Now, Samia would run this lab number 5 in the next hands-on session. Okay, but remember that you have access to the others, so you can still do them at your own pace. In addition to that, those same libraries, we ported them to Fabric. So if you are using Fabric for your experiments and you want to learn about P4-DPDK, you can go to the Fabric website, and there is something called Artifact Manager. There is where you can see what are the experiments shared by the users of Fabric. And there we have those libraries available. So all you have to do is just you download. They will be available for you in your notebook. That's the interface that you use for Fabric to start running the experiment. And then you will be able to run all of them. What are the labs so available as of now? So we have 8 labs. The first 7 labs are using virtual NICs. So similar to what Sergio was showing, just purely software NICs. Now, lab number 8 will show you how you can deploy it with a physical NIC, a real hardware. So with this lab here, we'll show you how you can deploy a pipeline that you can start sending traffic at high rate. And you will see that you can issue or you can send traffic at 100 gigabits per second and the pipeline will be processing them. So it will not only show you how you do the programming for the pipeline itself, but also how you generate traffic at 100 gigs. You can use like tools like DPDK, packet gen, and others. So a very nice lab. I would strongly advise you if you are using or if you are planning to use Fabric to go over this lab. And we are in the process of developing more, so there will be some related to machine learning and other stuff, measurements and so on. So now I will hand it over to Samia to describe another application using P4-DPDK, and this is related to detecting and mitigating distributed denial of service attacks. So I'll stop the share, Samia, and then you can share your screen.
Okay, thank you. And there. You should now be able to see my PowerPoint presentation. And in these last couple of slides, I will be showing a demo about DDoS attack detection and mitigation using P4-DPDK pipeline. So similar to what Sergio have shown already, a P4-DPDK pipeline to build, but the P4 programs is coded to detect and mitigate these DDoS attacks. And also, as Dr. Kfouri has been introducing in the previous slides, there's a Fabric platform that we have used to implement this topology here. It consists of 3 main nodes. We have one host to send background traffic at a very high rate, around 100 gig. We have the P4-DPDK pipeline implemented on the second host, and on the third host we have it acting as an attacker, so it will be generating different types of attacks that the P4-DPDK pipeline is going to be detecting and mitigating. And the NIC that we have attached over these hosts are all Connect X6 NICs, and they support 100 gig. And of course, they support the PDK. And you can think of this NIC over here as what we have in this diagram, the first block, the smart NIC. And that's where all the incoming packets from the attacker or from the background traffic, they are being hashed into different hardware queues. And each hardware queue is pinned to a separate pipeline. So what we have seen now in the lab that Sergio ran a moment ago is one pipeline running and forwarding packets between 2 servers. But we can also parallelize the process among different CPU cores and have multiple pipelines running. And we have done that and evaluated the performance of the P4-DPDK pipeline with different number of CPU cores. How is this affecting the throughput? How is this affecting the packet loss, etc. But we can either have hard-coded values to detect if the number of packets received from the attacker have exceeded a specific threshold and mitigate the attack, or we can even either have the control plane grab these measurements, collect them, and use a linear prediction model to generate a rate limiting threshold and push it back to the pipeline so that we will be dynamically adapting to the behavior in our network and see whatever the network needs and feeding it with rate limiting thresholds based on the normal behavior of the network at this specific time. In this slide, we show some results from both to exhibit the ability of the system to mitigate different types of attacks in a diversity of ways. So we can see here in the first 3 attacks, we are receiving packets, but when they exceed a specific threshold, we are limiting the rate. So that's how we can see here this drop. So we are limiting the rate in different percentages, whereas for other types of attacks, we are either doing some connection tracking. So if this attack, for example, here it's a fin flood, and we can see that the attacker is aiming to terminate a TCP session that has not yet been opened. So the flow is not allowed at all. Whereas for other types of attacks also, we are checking if the number of packets received has exceeded a specific threshold per flow. We are blocking the flow entirely. So with P4-DPDK, we have the flexibility to program the behavior of our program however we want. But in this second experiment, I aim to show how the system is able to adapt to different normal behaviors or to different throughputs that have been observed, and also detect on the go some DDoS attacks or heavy flows. So we can see here in the first 10 seconds, the system is able to learn from the normal behavior or the normal activity of the network, and it will also generate an offset value, which is the allowed margin. So we are able to observe an increase in the throughput, but as long as it's within this specific allowed margin. But if the number of packets observed goes above this allowed value, the system is going to forcefully process only the number of packets that matches the allowed margin. And the attack is claimed to be terminated and finished when the observed throughput goes below the allowed margin. And here we can see that the system will adapt, and now we have a new allowed margin that the system is going to allow. And we can see here another DDoS attack has been initiated at time 30. And even if the attack is ongoing, and the attack we can see at time 40 is even aggravating, it goes up to 20 gig. The system doesn't claim the attack to be finished until it goes below the allowed margin. And all of this is happening while the system is still able to process 100 gig of throughput from background traffic. And here we have this demo just to showcase how things are happening. So we are running background traffic, and we can see that the number of packets being sent and received was around 100 gig. And when we initiate here an attack, we are going to perform rate limiting. So the number of packets that are received by the pipeline are not all processed, only 50% is being processed. So 10,000 packets are processed here in this example. Whereas if we have a heavy hitting, sorry, my mistake. So as we have a heavy hitting flow, okay, and we can see that, sorry. Okay, it's generated from a single flow. Only a certain amount of packets is allowed, and then the flow is blacklisted and it's no longer allowed. And for this fin flood attack, we are blocking the out of session flow, so it's detected as a flow that doesn't belong to an open TCP session. Therefore, this flow is entirely blocked and it's not allowed from the first place. On the right-hand side, we have background traffic running at 100 gigs. And on the right-hand side, we can see that we have the control plane calculating the allowed number of packets, pushing it to the pipeline. And here in the pipeline, we are going to start a flood attack. And once a flood attack is detected, the control plane is going to send some alerts, and also it is going to rate limit or push the rate to a specific to a specific level that matches the allowed number of packets. So we can see that the allowed number of packets is going to be decreasing, and only 100,000 packets are going to be allowed. And the system will resume to its normal behavior in this case.
All right. Thank you, Samia. So we're a little bit past the agenda. We're just 5 minutes. So we're gonna take a break now, 10-minute break, and then we will return back at 3:25 p.m. Eastern Time. And then we will start a new lab that's gonna be on how to calculate these inter-arrival times. We will see concepts like hashes and registers. And finally, we will conclude about SmartNICs. So let's take a break and we will be back again at 3:25 p.m. All right, welcome back, everyone. So now we will move to the next session, hands-on session, and this is gonna be, again, on calculating packet inter-arrival times. It's gonna be led by Samia. So Samia, please feel free to share your screen and get started.
Okay, so I will be going over the second hands-on lab entitled Calculating Packet Inter-Arrival Time Using Hashes and Registers. And this lab is the lab 5 in the P4-DPDK lab series. So really this lab aims at shedding the light on diversity of features that the portable NIC architecture in P4 supports, among which are timestamping, hashing, and registers. So we will be calculating the inter-arrival time, which is the time gap between two consecutive packets that belong to the same flow. And basically, I know that this could be a little bit very straightforward, how to calculate the inter-arrival time of packets, but really these are things that can be used for more complex applications. In cybersecurity, when you want to deal with some cybersecurity applications or applications related to encrypted traffic, similar to what Amit has shown in his demo. So he was using the inter-arrival time as a feature, later on feeding it to a machine learning model and doing more complex stuff with that. So this lab really aims at placing your hands on these features. And again, since the inter-arrival time is the time gap between two consecutive packets belonging to the same flow, then we have to identify a flow. And in this case, we would be using hashing to identify a unique flow. So the hashing algorithm will take a series of bytes, and for each series of bytes, it's going to calculate a hash value, and this hash value is going to be used to as an index in the register where we will be saving the inter-arrival time. And to identify a flow, we will be looking at the 5-tuple, which is the source and destination IP addresses, and the source and destination ports, and the protocol. So this is like just the workflow of what we will be doing in the P4 code. So as soon as a packet is received, we'll be hashing the 5-tuple, and the output of the hash function is going to be a hash value that is going to be used as an index in a register. And this index is going to be pointing to the last timestamp that belongs to this specific flow. And when the second packet is received, we will be calculating the inter-arrival time by calculating the difference between the last timestamp and the current timestamp. And finally replacing the last timestamp by the current timestamp so that we will be able to perform the same for upcoming packets. This is going to be the lab topology. So we will have the P4-DPDK pipeline connected to 4 different hosts, each in a different namespace. And host 1 is going to be sending packets to host 2. Host 3 is going to be sending packets to host 4. And this is to showcase how we are able to identify different flows and calculate the inter-arrival time for each. So host 1 is going to be sending packets to host 2 at a different rate than host 3 is going to, than the rate at which host 3 is going to be sending packets to host 4. And host 1 and host 3 as senders are going to be sending packets with a custom header added inter-arrival time. This is just for some simplicity and to showcase the objective of this lab. We'll be appending the inter-arrival time value to this custom header, and we will be reading it at host 2 and host 4. So now, I assume if you have already logged in to NetLab, you are already in there, but still, if you haven't yet logged in, I'll be pasting this again in the chat, and you can use your email and your password, or even if it's your first time to log in, you can use the temporary password to set your email. Sergio will be handling any problems that you might be facing, so feel free to post here in the chat if you are facing a problem to log in. But okay, I see someone who has a previous reservation. If you are willing to do this lab along with us now, I advise you to terminate this lab reservation and schedule another one for this lab just to make sure that the environment is clear and that your machine is reset. So we'll be selecting now the P4-DPDK security lab series, and we'll be doing lab 5. And we can schedule a reservation. And once your reservation is done, you are ready to enter the lab. Okay, so we'll start by clicking on the client machine. And I will keep it side by side with the documentation. All right. Okay, so this is the content of the lab. We always start with an overview, the objectives. The introduction is something similar to what I have introduced in the slides, but a little bit more detailed. And the lab topology also has been discussed in the slides, so I'm gonna jump right away to where the lab starts. We're gonna start by opening the terminal and loading the programming environment in VS Code. So that's why I'm using the code command. P4-DPDK labs, and we are working with the lab within the lab 5 directory. Okay, so we are next required to go to the headers. Oh, sorry. To the headers file. And that's where we will be defining our custom header, which is the inter-arrival time header. So to declare a header, we're gonna have to write a header, and we're gonna call it, what we are doing here is setting the type of the header. So that's inter-arrival_t. And next, we are going to include the fields that are going to be included in this header. And we are going to be using one header that will hold the inter-arrival time value. And this is going to be represented with 48 bits. Underscore value. Okay. Next, in step 3, we will be appending this header that we have just created to the structure that includes all the headers that we have here. So we have the Ethernet header, the IPv4 header, and we are going to append the inter-arrival time header. And we are going to label it as inter-arrival. Okay. In step 4, we are going to be declaring the metadata that we will be using in our code. You can think of these as variables that you usually declare. And we will be starting by declaring the flow ID variable. And this is going to be represented with 32 bits. So I'm going to type bit 32. And we're going to label it as the flow ID. Next, we need a variable to hold the value of the last timestamp, along with also the value of the current timestamp. And these are going to be represented in 64 bits. And we will call the first one last timestamp. The second one is going to be the current timestamp. Okay. And finally, we need a variable to hold the value of the inter-arrival time that is going to be calculated by taking the difference between the last and current timestamp. Inter-arrival underscore value. Okay. With that, we are done with the headers file. Don't forget to save. Ctrl S to save. And we will be moving on to the control block of the P4 code. And that's the block that really holds all the packet processing logic that we will be specifying. Whatever we specify before the apply block is going to be some tables, actions, or even registers, functions, and everything that will be included within the apply block is going to be invoking whatever we have declared above it. So in step 2, we are going to start by creating our hash function. And we will declare it by first typing hash. And here we are going to be including the hash algorithm that is supported in the PNA architecture of P4-DPDK, and that's CRC32, which is the cyclic redundancy check 32 hashing algorithm. It's a checksum algorithm that hashes bytes into a sequence, every sequence of bytes into a 32-bit hash value. And that's why we have to specify that this hash function is going to be generating a value represented in 32 bits. Okay. Then we will have to specify the hashing algorithm that we are going to use. So that's PNA underscore hash algorithm underscore T dot CRC32. And then we are going to label it by just simply hash. You can call it hash1, hash2. This is user defined here. Okay. And in the upcoming step, we will be invoking this hash function to compute the flow ID. And we are going to declare this in an action. You can also think of this as a function. So we're going to call it compute flow ID. And this function doesn't take any input arguments. And the behavior invoked in this function is the following. So we will be writing the hash value to the flow ID variable or metadata that we have declared. So meta.flow ID. And we will be invoking the hash function that we have declared a moment ago in the line above. And we will be using the getHash method to compute the hash value. And here we have 3 parameters that we have to specify. So first, we will specify the minimum value that this hash function can generate. Then we are going to specify the data that we are hashing. In this example, we are hashing the source ID and the source address and the destination IP address to specify that this is a unique flow. And then we are going to be setting the maximum value that this hash function can generate. And in this case, we chose 1024. So we'll be casting the value of 0 to 32 bits. Okay. Bit 32. And there goes the value 0. And then in between curly braces, we are going to be specifying what values we are going to be hashing. So from the header structure, we are looking at the IPv4 header and specifically the source address field. Along with also from the header structure, IPv4 header, and we are looking at the destination address field. Finally, the maximum value. Okay, and that's it for the compute flow ID action. In this section, we are going to be computing the inter-arrival time. So we will be first starting by declaring a register. And we have agreed that the metadata that we have declared, like the flow ID, last timestamp, and the current timestamp, are variables that are only available throughout the lifetime of the packet. But if we need to save a value and we want this value to be available throughout the operation of the pipeline, we will need to store it in a register. And that's why we need to declare one here, register. Then we will have to specify in this first parameter the width of the cell of this register. So this register has multiple cells, and in each cell, it can hold a value of 64 bits as we are specifying here. Okay. In the next parameter, we will be specifying the length of this register. So how many possible cells can this register hold? In this case, we will specify bit 32, which means that this register can hold up to 2 to the power of 32 cells. But we will also specify here that we only need 1024 cells because our hash function is going to be generating flow IDs, which are going to be used as indices in this register only from 0 to 1024. So in this case, to be more efficient, we can even specify that we want the length of the register to be represented with 10 bits. So 2 to the power of 10, that's 10 to 1024. But in this lab, we're just gonna leave it like that for now. And we will label this register as reg last timestamp. Okay. Next, we'll be declaring an action in which we will be computing the inter-arrival time. So we will call this action get inter-arrival underscore time. Again, it won't take any input arguments. Okay. So to do so, we are first going to start by getting the value of the last timestamp, and we are going to assign this value to the last timestamp metadata. Last timestamp. And we will be reading the value of the last timestamp from the register. Okay. And we will be using the read. So we'll be setting .read as a method here. And we will be reading from a specific index. And this index is pointed out by the flow ID. And that's why we will be casting the flow ID to bit 32. Okay. And this is also because that in this register, the index has to be represented with 32 bits. And we are computing the flow ID with the hash function that generates this flow ID in 32 bits. Okay. And then after we have the value of the last timestamp, we need to grab the value of the current timestamp. Okay. And we will assign it to the metadata.current timestamp. And to grab the value of the current timestamp, we will have to use the standard metadata. And this is represented in 64 bits. So bit 64. And to grab the timestamp, we will have to do the following: istd.timestamp. Now, since we have in hand the last timestamp and the current timestamp, we are ready to compute the inter-arrival time. But first, we'll be checking if the last timestamp is equal to 0 or not, because for each flow, this is going to be the case. The last timestamp, the register is initially equal to 0. So first, let's check if the last timestamp is equal to 0. Meta.last timestamp. If it's not equal to 0, then we will be computing the inter-arrival time. Okay. So, and to compute the inter-arrival time, we will be assigning this value to the inter-arrival time metadata, inter-arrival value. And that's the difference between the current and the last timestamp. Otherwise, we will just set the first inter-arrival time value to be equal to 0. This is going to be only the case for every first packet received from every flow. Okay, and finally, after computing the inter-arrival time value, we can update the value of the timestamp in the register. So we are going to write to this register, reg less timestamp. We are going to write to this register. And to write to a register, we will first have to specify at which index we are writing. So that's the flow specified by the flow ID. Okay. And we will have to specify also the value that we are writing at this specific index. Meta dot current timestamp. And that's it in terms of declarations. Now we will have to invoke these functions in the apply block. And what we are going to be doing first, let me check first if I have any typos before I yeah. Low ID. Okay. I might have some typos, but when I run the compiler, it's gonna be smart enough to point them out. Okay. So in the apply block, we'll be first checking if we have any IPv4 headers. So from the header structure, we will be looking at the IPv4 header, and specifically, we are going to invoke the isValid method to check if this header exists. Okay, I'm sorry. Next, we will be checking if the custom header that the sender will be appending is also there. So we'll check if in the headers we have the inter-arrival header and also is valid. Okay. And if so, then we are going to start by computing the flow by invoking the compute flow action that we have declared. Then we will be also calculating the inter-arrival time, and that's using the get inter-arrival time action. Finally, after we have the inter-arrival time value, we will have to write it to the inter-arrival time value that is within the inter-arrival header. So we're gonna access the structure header, inter-arrival value, inter-arrival, and then, because this is the label of the header, and inter-arrival value. Okay. And we are going to be casting the inter-arrival value to 48 bits. Okay. Okay. And here. Meta dot inter-arrival value. Okay, I will be checking for every line if there's a typo. So also we have a typo here. Okay.
Lamia, also the parentheses after you have to close it before you open the curly brace on line 51.
Yes. There.
And yeah, you remove it after the ending curly brace on line 55.
Fine. So we are left with one more line here, and this is to apply the forwarding table, and this table is there to forward the packets from one host to another based on the MAC address, and this is going to be in the forwarding dot apply. Okay. So again, I will just repeat. In the apply block, we are checking for an IPv4 header, and then we are checking for the inter-arrival time header. We are calculating the flow ID, which is going to be used in the to get the inter-arrival time and also write the value to the register. And finally, when we have the inter-arrival time value, we are going to be writing it to the inter-arrival header. Okay. Finally, we are going to be saving, and we will be compiling the code using the P4-DPDK compiler. So if you cannot see the terminal, you will have to click on terminal and open a new terminal. Okay, DPDK. We'll specify the architecture, which is PNA in this case. We'll pass the P4 code that we are compiling, main.p4, and the output is going to be labeled as lab5.spec. Okay, if we don't have any errors here, then everything should be fine in the code. Now we will open the terminal again. We need to enter the super user mode. The password is password. And instead of going through all the steps that Sergio has already explained in the first lab, we will be running here a script that is called run pipeline. It's a shell script, but if you inspect this shell script, it's going to be exactly what Sergio has done in the first lab. So we will first go to the lab directory, lab 5, and that's where the script is. Okay, we can see that in this pipeline we have 4 devices because we have 4 hosts attached in our topology to the pipeline. And now we are going to build this topology by opening a new tab in the terminal. Also, sudo su password, and we will have to also go to the directory of the labs, lab 5, and we will be also running a shell script to set the topology, but it's also identical to what Sergio has done to build a topology with 2 hosts. Instead of that, we are going to be connecting 4 hosts to the DPDK pipeline. Okay, at this point, we are ready to test the if the pipeline and the behavior of the code is as we have described it in the P4 code. So we will first start listening for packets at host 2. So we'll be mainly sending packets from host 1 to host 2. So host 2 will be sniffing at the interface, waiting for packets to be received. IP, network namespaces, exec h2, because we are executing the following command in h2. We are running a Python script Python 3 receive.py. And this -p parameter is just to use this this code among different labs. And here we are specifying that we want to append an inter-arrival header to this packet. So inter-arrival. So now host H2 is sniffing at its interface, which is labeled as DTAP1. Now we are ready to start sending packets from host 1 to host 2. So we will also need to go sudo su the lab directory. And this is where we will be executing a function, a command from host 1. And here we are also running this Python script, which is going to send, it's called send.py because it's going to be sending packets to host 2. And here we will have to specify the IP address of host 2. So that's 192.168.10.2. And also one more parameter that we will have to pass here is the amount of packets per second. And we are going to be sending 10 packets per second. And this is also a parameter to append the inter-arrival header. So if we are sending 10 packets per second, then we are expecting the inter-arrival time value to be 1 divided by 10, that's 0.1, and that's around 100 milliseconds. But we are calculating the inter-arrival time with nanosecond granularity. So this is going to be around 100 million nanoseconds. So now host 1 is sending 10 packets per second. We can go back to host 2 and check the inter-arrival time value, which is around the expected value, 100 million nanoseconds. Now, I will leave this running and I will open a new terminal. And this is where we are going to be now sniffing at host 4's interface. So sudo su password. Again, we need to go to the directory. And this is where we are going to be executing the command to sniff at host 4's interface. Host 4. Same command as before. Receive, Python 3. .py. And this parameter for the inter-arrival header. Okay, so now host 4 is listening at this interface, DTAP3. Now it's time to start sending packets to host 4, and we're gonna do this from host 3. Sudo su password. Labs, and we're gonna go to lab 5. IP net NS exec from host 3, executing a Python code, send.py. The IP address of host 4 is 192.168.10.4. And in this case, we are going to be sending packets at 20 packets per second. And enter arrival. So if we are sending packets at 20 packets per second instead of 10, so we are expecting the inter-arrival time to be chopped in half. If we were sending, the inter-arrival time was 100 million nanoseconds. In this case, it's going to be around 50. And we can go back to the tab in which we are listening at host 4's interface, and we can see that the inter-arrival time is equal to 50 million nanoseconds, whereas we are still computing the inter-arrival time of the packets sent between host 1 and host 2, and that's 100 million nanoseconds. So the aim here is to show that we have two different flows and we are calculating two different values for these two different flows using hashing, timestamping, and also the registers. And this brings us to the end of this lab, Lab 5. And I am ready to take any questions if you have any.
All right, thank you, Samia.
Thank you.
Is there any question on this? One thing I want to add is that here the inter-arrival header was being added by the sender. Now, in reality, it's not the case. In reality, you would have regular traffic without a special custom header being added to the generating flow. But that's still fine. I mean, you can still do the same thing. You can still compute the inter-arrival time. Instead of adding the end result into the header itself, you can send it somewhere. Like, let's say if you want to send some to the control plane, or you want to mirror some of the traffic, send them to another device, that also works. Okay, or if you want to calculate the average across a certain window and then take action on that average value instead of every single value, that's also possible. But here we are just adding to the custom header that was added to the packet at the center side. Okay. All right. Well, again, thank you, Samia. So we still have the last topic for today. This is going to be an introduction to SmartNICs. So I will share my screen. All right. Again, I just want to reiterate that all the slides are on the webpage. And then at the end of today, we're going to be also adding the recording for today, as we did for the day on Tuesday. And there's also at the end, there's a survey. We would appreciate if you can fill it and give us your feedback so that we can improve for future workshops. All right, so let's get started with the SmartNICs fundamentals. All right. So far, we've been seeing all these nice technologies, right, with P4 and DPDK to accelerate packet processing on the CPU. So this is very good to achieve like rates at the 100 gig for some packet processing. Now, we got to a point where even CPUs are no longer making progress in terms of speed. So what you see here is a figure, and this is a popular figure. You might have seen it in some architecture books, Hennessy and Patterson specifically. Around the x-axis, you have here the years, and then on the y-axis, you have the processor performance. And what you can see here is that in the early 80s, we were getting around 25% improvement per year in the performance of the processor. Then up until around 2003, it was 52% increase. Now, around 2003, Denner scaling ends. So Denner scaling is kind of like a law that says that as the transistors become smaller, their power usage drops proportionally, right? So this would allow the designers to pack more of them into the chip and then run them at higher speed without increasing the overall power. Now, with that, we see here around 2003, it ended. So this is because of like the physical and thermal limits, right? So we couldn't make any more progress here. So that turned the industry into multiple cores, right? So instead of having a single core, you have multiple cores to do the processing. But also that's limited as per Amdahl's law, which says that, well, you can add more cores to increase performance, but at the end, the performance is limited to the amount of parallelism. Like if you have a lot of data dependencies between the tasks, you're not going to be able to leverage a lot of parallelism there. And then, of course, Moore's law, which is the number of transistors. That's like a prediction back in the day. They said that the number of transistors per chip would double every 2 years. So this is no longer the case, no longer holding. And you can see now the performance is kind of getting stable. So we are no longer seeing that improvement that we were seeing in the past. So many think that because of that, now the only path moving forward is to go for domain-specific accelerators. We are calling them here DSAs. But essentially, these are engines that are specifically designed for a certain application domain, right? For example, for graphics, you have GPUs, right? For these packet processing, you have like ASIC-based packet processors and so on. So how does the network interface card look like? Well, historically, you only have basically a Ethernet and serial I/O. So we do some very basic processing. You receive the packet from the wire, right? You can see here the RX, TX. You get it from the network, and then you use DMA to move it to the server using the PCIe. Then another generation, it's called offload NIC. Some of them even call this offload NIC a smart NIC because smart NIC's definition is not very clear, but this offload NIC really is adding some additional fixed function components to offload some of the functions that are typically done on the host CPU. For example, calculating checksums, encapsulating or de-encapsulating segments, some of the TCP segmentation, they can be offloaded. So these are all implemented on fixed function components like in an ASIC at the hardware. And we are offloading those because previously these has been executed on the host CPU. So now we are relieving the host CPU and offloading some of those functions. Now the latest generation of smart NICs, sometimes called DPUs or IPUs, they use domain-specific processors to customize packet processing, and they have a lot of those packet processing accelerators. So you have one to program a pipeline, similar to what we were seeing with P4. But you also have others for like encryption or decryption or regular expression matching or compression. So these are all like domain-specific accelerators embedded into the hardware, and they're available for you, right? So here you see that when the packet comes, there's a embedded switch. We call it NIC switch or traffic manager. That switch job is to steer the traffic to the execution engine. So you can send the packet to that programmable pipeline, or you can send it to a certain accelerator to be encrypted, for example. But also you see that we have now CPU cores as well. So those CPU cores would make the smart NIC autonomous, meaning that it will have its own operating system. It's completely separate from the host. Eventually, of course, physically it's residing on the host, but it has its own operating system. The management is separated. Now, with that, what can you do? Like, why are we doing all of this? Because now we can offload many of the infrastructure functions as well as other like custom data processing functions to the smart NIC. This is a small taxonomy of some of the applications. For example, for security, you can offload some functions of the firewall or packet filters, intrusion detection and prevention. Maybe you want to do like DPI, the packet inspection. If you want to do TLS offload. For networking, maybe you want to offload the tunneling like VXLAN or Geneve. Telemetry, you want to see like some of the packets like inter-VM observability, you can get that now. Load balancing and so on. For storage, you can accelerate like the initiation of NVMe towards an NVMe target storage device. Compression. For compute, like machine learning, inference and training, caching, and so on. So a bunch of functions have been implemented there just to first accelerate them and then relieve the CPU at the host from doing this processing. I will just go over some of these applications here, right? Just to give you an idea of what has been implemented and what are some of the performance numbers that we were seeing. So, for example, if you're interested in cybersecurity, if we look at how data centers have been historically and how they changed nowadays. So if you look at the top left, this figure A, you have a perimeter-based security. This is mostly to inspect north-south traffic. So these are traffic coming out of a certain VM all the way to the outside network, and then from the outside network back to the internal network. So this is only for inspecting this north-south kind of traffic. But with the advances of cloud computing and microservices, containers, now you see a lot of VMs having to communicate with each other without really needing to exit the network. So this is called east-west traffic, right? You see that, let's say we have VM A and VM B here. They want to communicate with each other. They don't have to leave the network, right? Go all the way to the outside. So that security appliance that we had in the past is no longer enough because it doesn't have observability over the inter-VM traffic. So one solution was, well, we can have a centralized security and then force the traffic to go over that centralized security that we can place inside for inter-VM communication. This is sometimes called traffic tromboning. You see that term sometime in the literature. But the problem is, I mean, it's very clear. I mean, you have a lot of traffic now are being sent and you're consuming the bandwidth of your links just so that they go all the way there and then they come back to the destination. So what is the solution to that? Well, now we need to make this as a decentralized approach, right? So instead of having a central appliance here doing the inspection, we can create separations of those and then attach them as close as possible to the computing resources. So you can see here now we are adding those, think of them as like the security groups or the firewall functions that you can add directly to the VMs, right? So that's good. Now you are getting better visibility and you don't have to have the traffic traverse all across your topology. So from VM A to B, you can see now they can just take the, maybe like the closest switch in that leaf-spine topology. So where does SmartNIC come into play here? Well, now with these hypervisors there, we can have physical SmartNICs inserted, and then we can have the security inspection being offloaded to the SmartNIC. So here, it's been historically being done in the software. Now we are trying to offload that to the hardware to accelerate. So that's like the high-level kind of architecture, how it looks like. We're going to look more into what are actually those security functions being implemented. So intrusion detection and intrusion prevention. We know that a lot of the traffic has to be inspected, whether it is passively, like in an IDS, you just deploy it offline and you mirror traffic to it, or it could be inline, like in the IPS. Now, if it is inline mostly, let's say you want to do deep packet inspection, right? Typically, you can do that with the CPU cores. So you parse the packet, you send the payload, and then you do some of the searching there. That works. But now if your SmartNIC support like an accelerator for pattern matching, like regular expression accelerator, well, then you can offload that there. So that will increase the performance. But also another important function of these IDS and IPS is what we call bypass. And the idea here is that not all the traffic has to be inspected, right? So if you have a large data transfer, if you have, you know, YouTube flow or any kind of flow that is just, you need to have the performance there, but you don't have to inspect every single packet. Well, you can bypass that. And this is a function that's been, you know, well known in IDS and IPS systems. However, historically, it has been implemented in the software. So all the packets have to go to the CPU, and there you would do this sort of matching to see if you want to bypass or you want to do this deep packet inspection on the flow. Well, historically, again, all of it is on the CPU core of the host. Now, what we can do is we can implement that bypass function into the programmable pipeline of the NIC. So if some packets you feel like, okay, they don't have to be inspected, why do we want to bother the CPU and have it consume the resources there? So we can simply forward that directly into the hardware. And when we say here hardware, this is running at line rate. So if your NIC is 100 gig or 200 gig, you're going to get 200 gig. Only those flows that are to be inspected, maybe, for example, you can do something like, I want to forward the first 5-10 packets for inspection, and then the other packets for that flow shouldn't be forwarded. All of this can be programmed in this pipeline. So you only focus on part of the flow. And when you do that, you're not going to end up hurting the performance. So if you compare this against what you were doing before, all the packets have to go to the CPU cores. And even if you do the bypass, that bypass function is in the software. And if you don't want to bypass it, you have to implement DPI, deep packet inspection in the software. That takes a lot of processing power. So this is basically some numbers for this bypass function implemented in the Suricata intrusion detection and prevention system. So on the left-hand side here, you see this is the throughput in gigabits per second. If you implement this bypass function traditionally in the CPU core on the host, at best you can get around 45 to 50 gigabits per second. Now, when you offload it to the hardware, you get line rate here. This is, a 400 gig NIC, so you have two 200 gig ports. We are able to process all of them. So you see the performance improvement here. Not only on the performance in terms of like packet processing, but also now you are not using anymore the CPU cores of the host. So previously you would use, for example, let's say you have 4 CPU cores are being used to do this processing. Now you have 0 because they're not going to be used for that purpose at all. So now you are preserving the CPU cores for more user-related functions rather than consuming them on infrastructure-based functions. Palo Alto Next Generation Firewall also has that bypass function, and you can see here for this test, they tested with 100 gig NIC, and then you can see how it approaches the line rate, whereas with software, you can get at most close to 20 gig. Same with the CPU cores. Here you would waste 12 CPU cores, whereas with smart NICs, you don't have to consume those CPU cores. So lots of improvements there. What other functions? Well, cryptographic functions. Here we are talking mostly about encryption, decryption, hashing, random number generators, these kind of primitives that you find in like cryptography algorithms. So smart NICs today, they can support symmetric encryption, something like AES, but at the same time, you can do something like RSA, asymmetric encryption. You can have a true random number generated directly into the hardware. So you're not using any like external kind of inputs for that random number generator. Some benchmarking numbers. So you can see on the left-hand side, this is the throughput on the y-axis. On the x-axis, you have the number of connections. And we are evaluating here, what is the performance that you get if you are activating TLS, transport layer security? Well, if you have one connection and you are using TLS in the software, you see here it's mentioned KTLS. KTLS is the kernel TLS. So KTLS by itself is an offload of the current TLS from user space to the kernel. So when you see KTLS, means that this encryption, decryption is happening at the kernel level instead of happening at the user space. So you see here with one flow or one connection, you get maybe around 6-7 gig. When you offload it to the hardware in a smart NIC, you can go up to 20 gig. Now compare that with TCP, meaning that you don't have any overhead at all, right? There's no overhead at all due to the cryptography operation. So with one connection, these two are very close, although TCP is better. Like without encryption, you're still gonna get a little bit more than when encrypting with the smart NIC. But then as you increase the number of connections, you can see here, right? For example, for 8 connections, you go from 50 gig to 100 gig without TLS and without offload and with offload. So now you are getting the same performance as you would get even without encryption. In addition to the throughput, of course, you have to look at the CPU cores. Like with KTLS, yes, you can get up to 100 gig with 512 connections, but then you will see that you are consuming a lot of CPU cores to do these operations. Whereas with, when you offload to the smart NIC, you consume much less, half of that, or even lower cases. So we did some experiments here for research just to see, like, if I want to transfer a large data set, right? We are talking about like 100 gigs or 100 gigabyte data set, and we want that data set to be encrypted. You can see here on the x-axis, we have the number of flows. And the y-axis, you have the throughput in gigabits per second. Without acceleration, like with 32 different flows, I mean, you can get at best 18 gigabits per second. Now, modern CPUs now, they have their own AES, they call it AES and I, which is like instructions for AES, for encryption, decryption. So we are still using the hardware there, even on the CPU nowadays. You don't have to have like an additional device. It's this instruction set is being added to current CPUs. So you can see this is in the blue, but with the SmartNIC, you will be outperforming that, right? So you can see that there's an improvement when you offload to the hardware, even over using it with the instruction in the CPU. Because if you just encrypt using that special instruction in the CPU, now the CPU is busy trying to schedule with other type of instructions, and that would cause some performance issues. So for this test here, we used Globus or Grid FTP as the protocol to transfer the data set, and then we saw this improvement in the performance. What else can we do with cryptography? Well, the whole IPsec, right? The IPsec stack, you can also offload it. On the left-hand side, this is how traditionally you would do IPsec. So on the host, you would have the software that would be both the control plane and the data plane. So the management of, the security associations and all the other stuff that you would do is IPsec. That's the control plane side. And the data plane is where you actually receive the packet and you do the encryption and the other operations. So they were done in the CPU of the host, consuming a lot of processing power. Now the data plane, you can offload it to the SmartNIC of this IPsec, right? So data plane of IPsec in the SmartNIC, leveraging the accelerators. So you can use something like the crypto, the tunneling, something like VXLAN, for example, or any other tunneling protocol. They are now supported in the hardware of the NIC, so you can do that as well. So what you would do, instead of having the control plane on the host side, you can put it now in the CPU cores of the SmartNIC. So the management of this whole IPsec stack is going to be in the CPU cores running on the SmartNIC, and the data path, the fast path, is going to be in the accelerators of the SmartNIC. So you can see here the host has nothing to do with any of the encryption. And in fact, if you look at the data that you're sending, you can see here, you are sending plain data, and then it's getting encrypted in the SmartNIC and sent out on the wire, or maybe sent to another VM if you have like multiple VMs here. Whereas if you don't offload to the SmartNIC, you are doing the encryption here at the user space, right? At the application level on the host. So here, not only you will improve the performance, but also you are separating, you're making it more secure, right? Because you're isolating the host from the SmartNIC. Another example of deep packet inspection, this is a work primarily done by Ali. Ali is here, he's a PhD student working with us, and he's been using SmartNICs for accelerating deep packet inspection. So here, for example, we are interested in looking at the TLS records, and then from there, we want to extract the server name using this SNI field. And then after we extract that name, we want to do like searching to see if this is a malicious URL or this is a URL that shouldn't be contacted. This could be useful, like if you want to block command and control kind of communication, or if you have some malicious domains, you want to block them. So what we are doing here is this SNI is going to be matched using the regular expression accelerator in the SmartNIC. So that's also completely in hardware. And based on the result, if we have a match or no, we can decide if we want to drop or return the traffic to the switch and then process. Now here, this bottom part, I didn't talk about it, but this is a programmable switch that uses P4-2. And here is where we're doing some of the initial processing before we get it to the SmartNIC. I'm not going to go into all the details, but the key idea to understand here is that this pattern matching and signature matching, inspecting payload to see if there's some bytes there, you can accelerate them in the regular expression accelerator. What type of numbers can you get? So you can see here, this is a cumulative distribution function, CDF, of the packet processing time. The green here is without pattern matching. So that's basically just forwarding traffic, right? Without doing anything. And then if you do the regular expression matching in the hardware, it's this light blue. So you can see there's definitely a a little bit of an increase, but that's still much, much better than doing this deep packet inspection in the software, which you see here in this orange line, right? Well, the first thing to notice here is that on average, it's smaller. So 7.6 microsecond compared to 21 microsecond. But also you can see that it's more consistent. So you don't have this high variation in the numbers. And that's because when you do things in the hardware, it's more deterministic, right? What are some other engines? Well, compressing and decompressing files or data. So there's a accelerator for that in the SmartNIC. And it's really nice because you can decrease the compression and decompression time significantly. And also you can save some of the CPU power. So on the left-hand side, this is the CPU utilization. On the y-axis, on the x-axis, you have different compression and decompression algorithms. The first three here are run on the CPU host, right? CPU of the host. So that's the traditional way. And each one of those is a different data set. Because, you know, like compression and decompression, they depend on the actual type of data that you have there. So you see here how much of the CPU we are consuming, up to we're close to 100% here with this specific algorithm. But then when we offload it to the SmartNIC, we're getting much smaller than that. Like worst case scenario here is around 50%. Now, in terms of time to compress this data set, you can see that this is in millisecond on the y-axis, right? So this is 10 seconds, for example, this line here, whereas here we are getting it in 200-300 milliseconds. So order of magnitude improvement in the time to compress a certain data set. So we talked a little bit about tunneling and network offloads. So with tunneling, the idea is that you have some underlay networks as the physical network here, and then you want to create a virtual network on top of it. This is a very common type of thing you would do in a cloud environment or a certain data center where you want to separate the virtual networks. Typically, what you would have is this VTAP device, for example, for VXLAN. And this is just an endpoint that will do the encapsulation, de-encapsulation, right? Now, this function has been also historically implemented in software, even though some of the switches and devices support that offload, but you can now do it in the SmartNIC too. So you can offload this VTAP, meaning that when you do the encap and the encap, it's gonna be running into the hardware instead of the software. This is some performance numbers. So for 114 byte packets and 64 connections, right? This figure here on the left is showing the throughput in million packets per second. So you can see here the improvement, right? With traditional, we are not able to do that many packets per second. Whereas with SmartNIC, we are close to a little bit more than 60 million packets per second. Now, when you add the connections, so with 250,000 connections, so remember, those are 250,000 connections that you are doing this encap, de-encap operations for, the performance would go down a little bit. Well, as a conclusion, so we saw that the CPU performance growth have been slowed down with the end of Moore's law and then scaling. We are not seeing any more improvement at the CPU core level. Even with parallelism, you are still limited by, or with multiple cores, you're still limited by how much you can parallelize tasks. So SmartNICs or DPUs, data processing units, they're becoming very popular now to offload this infrastructure workloads. They combine domain-specific accelerators. We saw some applications like security, deep packet inspection, firewall functions, bypass, and so on. For network, something like encapsulation, de-encapsulation, IPsec, storage, and compute tasks, they are all being offloaded to the SmartNIC. And because we are using domain-specific accelerators that are implemented in the hardware, we are getting better performance, and we are relieving the CPU cores of the host for other applications for the users. And so far, I mean, there's a lot of interest in SmartNICs, and it seems that it's going to become an integral component in every network infrastructure. So far, mostly like hyperscalers, like, you know, public clouds are using them. Data centers, some data centers, Fabric, for example, the national test bed is using some of them. But because NICs are there, I mean, you would have a NIC anyway in your server. It might become integrated into a lot of the different networks, even smaller networks. And as we saw, like with the KTLS, for example, this is just a flag you activate. You don't have to rewrite the whole stack. So if you can just activate a flag and float to the hardware and get that performance benefit, then that's something that we see that it could be available in most of the network moving forward. All right, well, that's what I have for this set of slides. Is there any questions or any comments? No? Okay. All right, so we're at the end of day number 2. Thank you everyone for joining. I hope you enjoyed this workshop, and I would again appreciate if you can fill in the survey that you see here at the bottom of the agenda. We will be uploading the recording. So the recording for the first day is there. We'll upload the recording for today, sometime later tonight. And if you need extension to access the labs for more than 6 months, you will have it for 6 months for now. Feel free to send us an email and we can extend that for you. And if you need also help connecting to the Fabric testbed, as Paul was mentioning earlier today, feel free to send them an email or just look at the forms in the Fabric website, and you'll be able to connect there. And all these experiments that we talked about here, you'll be able to run them there. Dr. Ticigno, if you're there, do you have anything you want to add? I don't see, yeah, I don't see him here. All right, well, again, thank you all for coming. Have a good rest of your day. Thank you. Thank you, George. Absolutely, Ravi.